Out of every single object scattered across the vast cosmos, from drifting planets to burning stars and massive galaxies, absolutely none are as bizarre, puzzling, or deeply intimidating as black holes. These entities are the most mind-shattering phenomena in the entire universe. They possess the terrifying capability to gulp down an entire star, swallowing it completely whole and completely undamaged. They unleash incredibly potent streams of cosmic energy, spewing vast amounts of matter deep out into space. Initially, these monsters were only found written on sheets of paper. They were scrawled out on the backside of an envelope as nothing more than a few squiggly pen marks. They emerged as a highly eccentric solution to a mathematical problem that seemed entirely impossible to decipher. This mathematical mystery was so profoundly strange that even Albert Einstein himself found it impossible to accept that black holes could actually exist in the physical world. In fact, the broader scientific community refused to believe for many decades that these objects were real. People firmly argued that the natural world simply did not function in such a bizarre manner. Nevertheless, as time marched forward, dedicated researchers began to closely inspect black holes by meticulously monitoring the violent consequences they inflict upon their immediate cosmic neighbourhoods. Slowly but surely, the pile of undeniable verification began to accumulate. We finally discovered the indisputable confirmation of a monstrous black hole that contains millions of times the total mass of our own Sun. Because of these cutting-edge scientific breakthroughs, we can confidently declare that we have achieved it. Black holes are entirely real, an astounding realization that caused even seasoned experts to think it was completely wild, prompting them to exclaim, "Holy cow!" But what are these phenomena in exact scientific terms? If humanity possessed the technology to journey across the cosmos and visit one directly, what incredible sights would meet our eyes? Furthermore, by wielding such unfathomable dynamic power, do black holes somehow dictate and sculpt the fundamental framework of the entire cosmos? Is it truly possible that our very existence and the existence of everything we know would be completely impossible without them? It is undeniably quite an extraordinary expedition to embark upon. Welcome to the ultimate black hole apocalypse, broadcasting right now on this special edition of There Exist Truly Apocalyptic Entities Scattered Throughout the Vastness of the Cosmos, functioning as literal engines of absolute devastation that are both profoundly threatening and deeply shrouded in secrecy. These entities are known to us as black holes. The dedicated astrophysicists, who spend their entire lives analysing them, find their properties to be completely jaw-dropping. It is a well-known fact that black holes possess a unique ability to completely scramble and expand your mind. Many researchers remain perpetually astounded by the mere fact that these bizarre entities genuinely exist within our physical reality. Black holes thoroughly break and contradict our most fundamental comprehension of the natural world. They stand uncontested as the single greatest unresolved enigma in the entire universe. They are completely invisible to the naked eye, yet they wield a degree of power that stretches far beyond what human imagination can grasp. They are fully capable of ripping a massive star into tiny, shredded pieces. In absolute reality, a black hole will aggressively consume quite literally anything and everything that happens to cross into its gravitational trajectory. If you ever found yourself exploring deep space, you would most definitely want to steer clear of them at every single cost. Incredibly, black holes even possess the power to physically manipulate and decelerate the forward flow of time itself. Though they were once dismissed as far too outlandish to ever actually exist, black holes completely fracture and shatter our foundational concepts of modern physics. Yet, based on the groundbreaking information we are currently gathering, it appears they might actually be a mandatory prerequisite for the universe as we know it to even exist in the first place. They may very well turn out to be the most vital and definitive main characters operating across the cosmic stage. What exactly are these highly eccentric and immensely forceful cosmic phenomena? Where can they be located? How do they operate? And in what ways do they exert absolute dominance over the behaviour of the entire universe? The grand scientific quest to locate and decode black holes is actively underway, and it promises to be a remarkably wild and unpredictable safari across the deep cosmos. It will transport us to alien environments where every single thing you believe you understand will be fundamentally pushed to its limits. We are travelling to frontiers where the fabric of space, the progression of time, and reality itself manifest as significantly stranger than the most creative science fiction stories. And we are initiating this epic exploration at an incredibly unexpected and mundane destination. We find ourselves right here at a highly isolated and distant spot situated within Washington state. It is at this very location that a radically innovative and unprecedented scientific trial has successfully recorded the presence of black holes for the very first time in human history. This monumental achievement originally traced its roots back over half a century ago. It began when a tiny group of deeply forward-thinking academics dared to conceptualize a highly complex methodology that relied on machinery that had not even been created yet. They were actively hunting for an elusive cosmic phenomenon that absolutely no one could state with any degree of certainty could ever actually be located. The entire experimental endeavour was incredibly audacious and saturated with immense professional risk. Falling short of their goals could easily result in their entire professional lives being permanently ruined by the stigma of failure. But they did not stumble. Right here, within the walls of these specialised laboratory environments, they managed to secure an utterly astonishing breakthrough. In the quiet, pitch-black early morning hours of September 14th, in the year 2015, their ultra-sensitive instruments successfully captured a profound interstellar communication. To human eyes and ears, this historic data transmission looks and sounds exactly like a tiny, brief audio chirp. Yet, despite its deceptive simplicity, that isolated chirp is an epoch-defining, monumentally historic event. The subtle gravitational signal had crossed a mind-boggling expanse of over 1 billion light-years of empty space just to finally reach our planet. Its journey commenced in an incredibly distant and unreachable corner of the deep cosmos. And the profound story that this signal conveys to us is this. Somewhere out in the massive universe, well over 1 billion years in our past, a pair of incredibly colossal black holes became permanently locked in a deadly, inescapable orbital dance. Closer and closer they spiraled toward one another. They swirled around a common centre faster and faster with every passing moment, until they finally collided with unimaginable violence, slamming directly into each other. This cataclysmic impact instantly generated massive ripples that began radiating dynamically outward through the cosmos. They spread precisely like the acoustic vibrations dancing across the surface of a struck drum. It was a literal ringing sound vibrating directly through the very foundational mesh of space itself. The unimaginable smash generated a colossal explosion of energy, unleashing an output that was a staggering 50 times greater than the combined power of every single star in the entire observable universe. It did not radiate a surge of heat, visible light, or traditional sound waves, but rather a pure, raw ripple of gravitational energy. This ripples of gravity immediately began tearing its way across the cosmos, travelling at the absolute universal speed limit, the speed of light. The ripple sprinted past countless stars. Back on Earth, giant supercontinents were just beginning to piece themselves together. Primitive, microscopic living entities had only recently emerged in our oceans. Meanwhile, the wave kept washing over one vast galaxy after another, continuing its endless journey. As massive dinosaurs ruled the landscapes of the Earth, the gravitational wave was still relentlessly zooming forward. It zipped effortlessly through colossal interstellar clouds of cosmic dust, and then it finally began to close the distance toward our own home, the Milky Way galaxy. Back on our world, the Great Ice Age was just starting to take hold. Our early human ancestors were living as primitive cave dwellers, meticulously painting primitive images onto cavern walls. The ripple eventually reached the stars situated in our immediate interstellar neighbourhood. By the time it passed those stars, a young Albert Einstein was sitting in a classroom as a simple 6th grade student. The wave continued its approach, closing in as near as the Alpha Centauri star system. As the clock struck midnight on September 13, 2015, the boundary of the wave was located as close to us as the planet Saturn. Finally, a full billion years after those two black holes originally smashed into each other, the space-time ripple completed its journey and reached Earth. It slammed directly into a pair of highly revolutionary, completely unprecedented scientific tracking facilities. These were the exact locations of that incredibly bold research project. This state-of-the-art facility is known as LIGO, which stands as an acronym for the Laser Interferometer Gravitational Wave Observatory. The highly ambitious project, which required a grueling 50 years of continuous scientific dedication to fully realise, had finally claimed the ultimate cosmic prize. In doing so, it successfully unlocked a completely unprecedented methodology for human beings to investigate the vast universe. For a span of 4 centuries, virtually every single piece of astronomical data we have collected from deep space has travelled to us via some specific manifestation of electromagnetic energy. That tiny recorded chirp represents something entirely distinct. The phenomenon that physically impacted the planet Earth in September of 2015 was a pure gravitational wave, a literal compression and elongation of the foundational fabric that constitutes space itself. It generated absolutely zero light. No traditional telescope, no matter how advanced, could ever hope to visually capture that collision. Humanity required a completely reimagined category of cosmic observatory just to possess a chance of measuring it. That single wave serves as brand new, unmediated verification of one of the most baffling secrets in our cosmos: black holes. The vast majority of people have at least heard the term black hole before. We know them as completely unseeable, immensely dominant entities. In these discussions, we are referencing astronomical objects that can easily contain up to 1 billion times the total mass of our Sun. They are genuine physical objects that possess an entirely infinite level of density. They have no true beginning and no true end. They relentlessly drag all nearby matter into their depths. They even drastically twist and warp the trajectory of passing light rays. If you were to dare to venture close to one, the very progression of time would start to fundamentally distort. The local gravitational field is so incredibly fierce that any clock brought near it will begin to tick at a drastically slower pace. Time will decelerate so extreme for your personal perspective that you would literally be able to sit back and watch the entire ultimate timeline of the future universe unfold right before your eyes. However, if you actually tumbled directly into its depths, you would be instantly stretched out until you were as thin as a single strand of pasta. The absolute fabric of space and time would snap you like a fragile wooden toothpick. In the modern era, humanity understands a great deal more about the nature of black holes than we ever have at any point in our history. Yet, a strange paradox exists. The more data we successfully gather, the more profoundly confusing and mysterious these entities become to us. They stand as the most deeply bizarre and exotic structures in the known universe. The reality is that we currently do not even possess the foundational framework of physics required to accurately describe them. No matter how deeply or comprehensively you attempt to comprehend them, they ultimately remain completely beyond our reach in a fundamental scientific sense. It is clear that black holes have earned a profoundly terrifying and fierce reputation across the globe. If you ever find yourself in need of a truly menacing antagonist for a Hollywood science fiction blockbuster, you should immediately cast a black hole in the role. But if we step out of the movie theatre and look at absolute reality, what exactly defines a black hole? And through what processes do they actually form? You might naturally visualise a black hole as being a solid physical object, but that is a major misconception. It is not a solid object at all. Instead, it is a literal tear or hole torn directly into the fabric of space itself. It represents a specific location in the cosmos where there is absolutely nothing present. There is nothing there whatsoever, except for an isolated concentration of gravity. This is gravity manifesting at its most intensely concentrated, overwhelming and absolute extreme. So if the entire concept of a black hole is fundamentally centred around the physics of gravity, and specifically gravity operating at its most radical limit, we must ask a foundational question. What exactly is gravity? Every single one of us is incredibly intimately acquainted with the phenomenon of gravity. It dictates our lives every day, and it rules over our physical existence. Even so, for an incredibly vast stretch of human history, the exact mechanics of how gravity genuinely functions remained one of the absolute greatest mysteries to science. Well over 300 years ago, Sir Isaac Newton became completely obsessed with monitoring the precise conduct of physical items while they were in active motion. Through years of rigorous study, he eventually mapped out his world-famous laws of motion. Those equations operate so incredibly well that modern engineers still rely on them to this very day. However, Newton's mathematical formulas suffer from a major limitation. They can only accurately describe the real-world consequences of gravity, but they are entirely unable to explain what gravity actually is at its core. And this exact theoretical gap is precisely where the genius of Albert Einstein enters the historical timeline. Very much like Newton before him, Einstein spends an immense amount of time deeply analysing the behaviour of physical objects experiencing movement, and he begins to deeply question the true fundamental nature of gravity. He asks, is it truly a physical, pulling force, or could it potentially be something entirely different? There is a very specific physical puzzle that deeply bothers Einstein. Consider this simple fruit, an apple. I am completely unable to physically displace or move this apple without physically making contact with it. Yet, if I choose to simply let go of the apple, it immediately begins moving directly toward the surface of the earth. But what would happen if I theoretically removed my hand and then completely removed the floor of this room, and then also removed the basement beneath that and every single floor below it? What would occur next? The answer is that the apple would just keep plunging downward forever. Einstein experienced a profound realization. He understood that the mystery of gravity was fundamentally linked to the physics of falling. Now, if I take the apple and actively hurl it across the room, it will fall toward the ground along a clearly visible curved trajectory. But let us imagine that I possess the ability to launch this apple at a vastly accelerated rate of speed. Eventually, if I can manage to get the apple travelling incredibly fast, let us say at a staggering velocity of 17,000 miles per hour, a fascinating phenomenon occurs. The curved arc of its downward fall will perfectly match the physical curvature of the planet Earth itself. At that point, the apple is officially in a state of stable orbit. It is continuously falling freely around the planet, operating in the exact same physical state as the International Space Station and the trained astronauts residing inside it. According to Einstein's revolutionary perspective, the apple, the massive space station, and the astronauts are all experiencing pure freefall along a naturally curved trajectory embedded within space. And what is the specific entity responsible for making that spatial trajectory curve in the first place? It is the sheer mass of the Earth. Einstein formulated an incredibly elegant, supremely uncomplicated mental concept. His big idea was that the literal fabric of space and time is physically warped and bent by the presence of the Earth, by the immense weight of the Sun, and by every single object that possesses mass in the entire universe. Therefore, based on Einstein's profound understanding, the inherent mass of every single physical entity causes the literal space surrounding it to physically warp. And that specific insight was Einstein's true masterpiece. In his new universe, traditional pulling forces do not actually exist anymore. Instead, you simply have massive cosmic objects physically distorting space-time, while all other surrounding objects merely coast along, pursuing the absolute straightest possible path available through that warped geometry. Every single object moving through the universe is just following the geometric bends carved into space. So how does the Earth successfully manipulate the motion of the apple without ever physically touching it? The answer is that the mass of the Earth warps the surrounding space, and the apple merely glides freely along those pre-existing geometric curves. That exact conceptual framework, according to Einstein's world-altering general theory of relativity, is the true definition of gravity, warped space. And that specific model of gravity, which states that a material object forces the surrounding space to warp, is the exact concept that leads us directly to the theoretical existence of black holes. However, historical accuracy dictates that it was not actually Albert Einstein who first managed to draw the definitive link between the mechanics of gravity and the existence of black holes. That honour belongs to an entirely different researcher. Karl Schwarzschild was a highly brilliant German astronomer who served as the esteemed director of the Potsdam Observatory located in Germany. Ever since he was a mere teenager, he had possessed a deep fascination with mathematically mapping out the highly intricate details of planetary pathways. When Einstein finally unveiled his completed theory of gravity to the world in the year 1915, Karl Schwarzschild was not sitting comfortably in a university office. Instead, he was actively serving in the German military, tasked with calculating complex artillery paths amidst the violence of World War I. Incredibly, just a few short weeks after Einstein had officially published his historic research papers, Schwarzschild managed to get his hands on a copy. Despite being stationed directly on the brutal Russian front, he immediately set to work mapping out the precise gravitational field surrounding a perfectly spherical star. Einstein had only managed to approach the problem through a complicated series of rough approximations, yet Schwarzschild, sitting directly in the middle of a war zone with deadly bullets and explosive bombs flying all around him, calculated a flawless, exact mathematical solution to Einstein's highly complex equations and promptly mailed it to Einstein. Einstein was completely blown away by the letter. He had not even remotely conceived that it was mathematically possible to solve those highly sophisticated equations in such a perfectly exact manner. But Schwarzschild was not finished with his calculations. Deep within his precise solution to Einstein's equations, he stumbled upon a deeply bizarre mathematical reality that Einstein himself had completely failed to foresee. Schwarzschild realized that he could mathematically compute a highly peculiar, specific distance stretching away from a heavily gravitating object. This specific distance represented a definitive, absolute boundary in space. Through pure mathematics, Schwarzschild mentally compressed the entire massive bulk of an object, such as a star, down into a single infinitely small point. Then he meticulously calculated precisely how that highly concentrated mass would bend the surrounding space and warp the pathways of light rays travelling past it. As he used his mathematical models to theoretically fire particles of matter or beams of light directly toward this single point, he noticed something stunning. There existed a distinct invisible boundary encircling the point, and the very moment any particle crossed it, it would simply stop moving entirely. The particles vanished from existence, and time itself ground to an absolute halt. Schwarzschild had uncovered a shocking physical truth. If you compress a concentration of mass down into a tight enough space, it will warp space-time to such a radical extreme that it creates a localized region from which there is absolutely no return. Anything and everything that crosses over that threshold will be permanently imprisoned, completely stripped of any capacity to flee, a rule that applies even to light itself. It functions exactly like those cheap roach motels. You can easily check into the room, but you can never ever check back out. Once your trajectory carries you across that definitive border, even if you glide through it completely smoothly, there is absolutely nothing you can do to escape. There is no action you can take to send a signal to the outside world. It transforms into a highly bizarre, permanently isolated segment of space-time. What Karl Schwarzschild had successfully demonstrated through pure numbers is that if you compress any given amount of mass into a sufficiently tiny volume, you will inevitably form what we call a black hole. Astoundingly, Albert Einstein, the very man whose own theory of gravity explicitly predicted this exact phenomenon, found himself entirely unable to believe that such an object could ever actually manifest in the real world. Einstein was convinced that the natural world would simply never behave in such an absurd fashion, and he deeply disliked the entire concept. Tragically, Karl Schwarzschild became severely ill and passed away shortly after, never receiving an opportunity to further study his own historic discovery. By the time November 11th, 1918 arrived and World War I finally came to an end, the highly eccentric, purely theoretical sphere that had been mathematically uncovered by Karl Schwarzschild seemed utterly destined to be lost to history. It appeared it would remain nothing more than a weird, obscure historical footnote. However, as the 1930s rolled around, scientists began to unlock the secrets of the atom. They started to uncover the precise mechanics of how fusing atomic nuclei together powers the burning of stars, a quantum process officially designated as nuclear fusion. With this new understanding of stellar energy, a small group of researchers began to ponder a fascinating possibility. They wondered if an extreme object like Schwarzschild's black hole could actually be forged naturally from the remnants of a dying star. But they knew this could not happen to just any ordinary star. It would require a truly gargantuan star. Stars are naturally brought into existence in large collective litters, and you always end up with a wide distribution of varied dimensions and masses. You will get thousands of modest small stars alongside a tiny handful of truly immense stars. These incredibly massive stars share a surprising number of similarities with living biological creatures. Just like human beings, stars experience distinct, predictable life cycles. While actively exploring the timeline of stellar lifespans during the 1930s, two brilliant visionaries named Subrahmanyan Chandrasekhar and J. Robert Oppenheimer made a monumental discovery. They uncovered the fact that the most monstrously heavy stars terminate their existence in a fashion that is radically different from smaller stars. The ultimate fate of a star's life cycle is completely dependent upon its total mass. The exact amount of mass a star possesses dictates exactly what will transpire the moment it finally runs out of its core hydrogen fuel reserves. Every single star in the cosmos initiates its life by actively burning hydrogen, which is the lightest and most basic atom in existence. They use extreme heat to fuse those basic hydrogen atoms into heavier helium atoms, steadily working their way up the periodic table to forge increasingly heavy elements. Throughout this entire process, the force of gravity is relentlessly trying to crush the star's entire massive structure inward. However, the mind-boggling amount of energy generated by core nuclear fusion pushes powerfully outward, successfully stopping the star from imploding. Stars manage to remain perfectly stable because there is a continuous balance. You have an outward moving wave of pressure generated by nuclear fusion perfectly cancelling out the relentless, inward crushing force of gravity. Modest smaller stars simply do not possess enough gravitational pressure to ever fuse elements that are heavier than helium. However, in the interiors of the most monstrously massive stars, gravity exerts such an intense crush that it forces the fusion of heavier elements, driving the chain all the way up to iron. Iron represents an absolute dead end for a burning star. An iron atom possesses an incredibly massive nucleus, packed with so many protons that the moment you attempt to fuse iron together, you do not get any energy back out of the reaction. Iron acts as a literal energetic brick wall for stars. Fusing atoms that are larger than iron fails to emit the necessary energy required to support the star's immense weight. And the very moment a star lacks a sufficient supply of energy from fusion to keep its structure inflated, there is absolutely nothing left to fight off gravity. At that exact moment, gravity wins the war, and as a result, the entire massive star undergoes a catastrophic collapse at a highly rapid rate of speed. Trillions upon trillions of tons of heavy stellar material come crashing downward in freefall. This falling matter slams violently into the ultra-dense central core and instantly bounces backward, violently blowing the star's outer layers out into space in a truly colossal explosion. This event is a supernova. The physics are simple. The more mass that remains, the more intense the gravity becomes. So, if the remaining stellar core left behind by the explosion is sufficiently heavy, the force of gravity becomes entirely unstoppable. There is absolutely no known force in the entire universe capable of halting the collapse. The core is forced to shrink down into an infinitesimally tiny dot. The core continues its dramatic implosion until absolutely all of its remaining matter is squeezed down into an unimaginably tiny, infinitely concentrated dot. This final destination is an infinitely small point in space. What you are left with is a genuine black hole. Even though this elegant blueprint makes complete mathematical sense on paper, the vast majority of mainstream physicists during that era remained deeply unconvinced and doubtful about the actual reality of black holes. Great scientific minds like Albert Einstein and Sir Arthur Eddington, who were considered the absolute most prominent and celebrated astrophysicists throughout the 1930s all the way into the 1950s, flatly refused to believe that these bizarre objects could actually exist in the physical universe. For a very long stretch of time, the entire concept remained locked away as nothing more than a theoretical solution, a confusing mathematical riddle that belonged in textbooks rather than the night sky. Because of this widespread professional disbelief, it took an incredibly long time for mainstream astronomers to even begin dedicating their telescope time to hunting for them in deep space. In fact, it was not until the revolutionary decade of the 1960s that the mainstream scientific community finally began to take the theoretical concept of a massive stellar collapse, creating a real black hole, completely seriously. During this pivotal era of cosmic discovery, a highly influential Princeton University physicist named John Wheeler, who had actually spent many years operating as an intense skeptic of the theory himself, began to popularise a specific, catchy moniker pulled from historical records to describe these unseeable entities. He called them black holes. Interestingly, the historical origin of the phrase black hole actually traces its roots back to the nation of India. Originally, the black hole was the dark name given to an incredibly notorious and feared subterranean military prison facility located in the city of Calcutta. Yet, even with a highly memorable new name capturing the public imagination, absolutely no one on Earth had successfully identified any physical evidence or verified sign of a real black hole out in the cosmos. Then, in the historic year of 1967, a brilliant and observant young graduate student named Jocelyn Bell made a stunning discovery that would alter astronomy forever. She uncovered the existence of a highly peculiar, unimaginably compact and dead remnants of a star that radiated an incredibly faint amount of visible light. This exotic object was officially designated as a neutron star, operating as the ultra-dense, freezing corpse left behind by a cataclysmic stellar collapse. The discovery of the neutron star instantly provided astronomers with a massive surge of confidence. It proved that if nature could forge such dense stellar remnants, then even heavier dead stars, which were mathematically predicted to cross the threshold into true black holes, might also genuinely exist out there in the dark. A full half-century after Karl Schwarzschild first used pure mathematics to demonstrate that black holes were a theoretical possibility, mainstream science had finally mapped out a definitive, natural life cycle that could realistically manufacture them. That natural forge was the violent death of massive stars. Consequently, we now understand that these gargantuan supernova explosions of incredibly heavy stars are the exact cosmic engines that manufacture black holes. To put it simply, any single star that is originally born in the universe with a starting weight that is roughly 10 times the mass of our Sun, or even higher, is destined to end its life by transforming into a black hole. Because of this predictable stellar cycle, our home galaxy is actually completely filled to the brim with small black holes, which operate as the invisible stellar corpses left behind by countless generations of ancient stars that have lived, died, and vanished across the eons. So, what exactly are these unseeable stellar corpses like in a physical sense? Let us imagine for a moment that I am actively navigating through the deep trenches of outer space, utilising an incredibly sophisticated, highly advanced piece of hypothetical technology designed for long-distance interstellar travel. This futuristic vessel allows us to easily journey directly to a real black hole, perhaps one located right inside our very own galactic neighbourhood. This specific black hole that we are currently approaching is not particularly large on a cosmic scale, possessing a weight of only about 10 solar masses, which simply means it contains exactly 10 times the total mass of our own Sun. And precisely like every single other black hole scattered across the universe, it features an unseeable boundary known as the event horizon. This manifests as a sharp, highly defined edge to the absolute darkness. This event horizon is the exact mathematical boundary that Karl Schwarzschild first uncovered through his calculations. A localized point of no return where the local pull of gravity is so fiercely dominant that absolutely nothing can run away from its grasp, not even a beam of light. And that terrifying boundary is precisely where our ship is heading. As our vessel inches closer and closer to the perimeter, some truly bizarre and mind-bending phenomena begin to manifest all around us. If you direct your attention to the very outer rim of the black hole, you can witness how the visual images of incredibly distant background stars are being radically warped, distorted, and smeared out into a glowing circle of light. This incredible optical illusion is a direct result of gravitational lensing. The black hole's unimaginably intense gravitational field physically twists and bends the pathway of travelling light rays as they pass nearby. This geometric distortion forces a single pinpoint dot of light from a distant star to briefly warp into a glowing ring that encircles the event horizon. At this stage of the journey, I have plunged deep into the black hole's massive gravity well, and our bodies are about to actively endure the physical consequences. The extreme concentration of local gravity actually physically slows down the forward progression of time relative to the steady passage of time back on the planet Earth. From the distant perspective of people watching me from Earth, my movements would appear to be drastically slower. However, if you look at it from my personal perspective, inside the ship, the passage of time back on Earth appears to be accelerating at a frantic, blinding rate of speed. Now let us imagine that I decide to push our exploration even further by actively exiting the safety of the vessel to execute a risky spacewalk. The profound way that the black hole manipulates and deforms the passage of time is about to become drastically more extreme and pronounced. From my position out in space, I can clearly witness the massive shadow of the approaching event horizon closing in. My spacesuit's safety beacon is flashing light pulses at a perfectly steady, normal rate from my point of view. But if you were sitting safely inside the observation deck of our starship and watching me drift away, an entirely different reality unfolds. The closer my body drifts toward the unseeable boundary of the black hole, the more slowly I appear to move through space. The individual flashes of light radiating from my spacesuit's beacon become spaced out by nearly infinite stretches of time. To your eyes, it looks exactly as though my entire body has become completely frozen in time. Yet, for my own personal experience, every single thing feels completely normal and fluid, even as my body actively crosses over the boundary of the event horizon. If you chose to park your starship outside and wait for a truly immense length of time, perhaps sitting there for millions or even billions of years, the crew would finally witness my image completely fade away and disappear into the void. And that quiet exit would be the absolute final glimpse anyone would ever have of me. What truly resides inside the interior of a black hole remains an absolute scientific mystery. And even if I manage to successfully uncover the truth during this plunge, I am completely locked away by the laws of physics, meaning I can never return to the outside world to tell you what I found. But I can share this single fascinating insight. Black holes may appear entirely dark and pitch black from the outside world, but on the inside, they can actually manifest as incredibly bright environments. As I fall, I can look backward and clearly watch all the radiant light from the surrounding galaxy that has tumbled into the hole right behind me, and that breathtaking cosmic view will be the absolute final thing I will ever see. Unfortunately, our thrilling excursion is about to come to a sudden and brutal conclusion. Now that my body has officially crossed over the threshold of the event horizon, I am experiencing a relentless, rapid freefall directly toward the absolute geometric centre of the black hole, which is the exact location where all of its immense mass is tightly concentrated. And as I fall closer, my body is beginning to endure a terrifying physical stretching sensation. Because of the extreme curvature of space, the gravitational tug being exerted on my feet is exponentially stronger than the gravitational pull acting upon my head. As a direct result, my physical body is starting to be violently ripped apart. I'm going to be systematically pulled and elongated until I am as long and thin as a single strand of noodle, a brutal astrophysical process officially designated as spaghettification. Ultimately, this extreme stretching will cause my entire physical form to completely break apart and disintegrate into its most basic, fundamental atomic particles. These isolated particles will then be violently crushed down into an infinitely small, localized point in space known as the singularity. This singularity represents a radical boundary where every single law and concept we currently understand about the nature of space and the progression of time completely shatters and breaks down. Or if we consider alternative theories, perhaps this black hole, which measures a modest 40 miles across its diameter on the outside, is actually as incredibly vast as an entire self-contained universe on the inside. If that is the case, as my disintegrated particles pass through the event horizon, they will seamlessly merge with the hot primordial cosmic soup of a brand new universal beginning. So that is exactly what the laws of theoretical physics tell us we would realistically endure and witness if humans ever possessed the ability to travel directly to a black hole. But how can the scientific community know these facts for absolute certainty? How do you systematically study and interrogate a cosmic phenomenon that does not emit any light and cannot even be seen with a telescope? The reality is that there are highly effective ways to investigate if a specific event is occurring somewhere in the world, even if you are entirely unable to view that event with your own eyes. Consider the famous example of Yankee Stadium. Let us say you want to figure out what is currently happening inside the walls of the stadium. Is there an active baseball game currently taking place on the diamond? From my position outside the arena, I cannot see the grass on the field. I cannot see any of the active players. And I cannot visually spot any baseballs or wooden bats. But despite that lack of direct vision, I can definitely tell if there is a massive wave of activity and movement happening all around the exterior of the ballpark. By analysing the surrounding environment, it becomes completely clear that something major is taking place inside. I can gather an immense amount of accurate data simply by carefully watching the behaviours and happenings occurring around the stadium. And if I look closely at the crowds rushing toward the gates, these individuals do look exactly like classic baseball fans. And that exact outside-in logic is precisely the methodology that astronomers utilise to study black holes. We investigate them by meticulously observing and measuring the undeniable physical effects they actively inflict upon their immediate cosmic surroundings. But what specific categories of physics effects are we looking for? Through what exact methods does an unseeable black hole accidentally reveal its hidden presence to our instruments? To answer that, we have to look back at history. Initiating just before the outbreak of World War II, a pair of monumentally historic scientific discoveries occurred that would completely and radically transform the entire landscape of modern astronomy. In the year 1931, a brilliant Bell Labs engineer named Karl Jansky began recording highly mysterious, persistent radio waves that were clearly emanating from the deepest trenches of outer space. Shortly after that discovery, the daytime and nighttime sky began to look even more alien and bizarre to researchers. This happened when a group of scientists successfully mounted primitive Geiger counters onto captured German military rockets and launched them into the upper atmosphere, only to discover that the empty cosmos is actually completely flooded with powerful X-ray radiation. These twin breakthroughs instantly provided astronomers with a set of incredibly potent new observational tools. These tools would completely revolutionise the global hunt for black holes, while dramatically expanding the boundaries of human vision. The reality is that the narrow band of light that human eyes can naturally perceive constitutes an incredibly tiny, restricted fraction of the broader electromagnetic spectrum. To put this into a relatable visual perspective, if you were to lay out the entire infinite electromagnetic spectrum across the massive length of the Brooklyn Bridge, the tiny slice of visible light that our eyes can naturally see would measure only a few inches wide. The broader reality of electromagnetic radiation encompasses waves of vastly different frequencies and physical traits. This includes long radio waves, microwaves, invisible infrared heat, standard visible light, ultraviolet rays, high-energy X-rays, and hyperviolent gamma rays. The sudden birth of radio and X-ray astronomy instantly tore open the sky, exposing a wild universe populated by incredibly dim or completely invisible objects that were actively blasting out colossal amounts of raw energy that absolutely no one knew existed. Scientists quickly began to realize that the cosmic canvas they had been looking at for centuries, which always appeared so incredibly placid, calm and quiet, as if nothing of note was happening, besides the slow looping of planets, was actually a mask. They uncovered the shocking truth that deep space was a theatre of absolute madness and chaotic violence. X-rays, by their very physical nature, originate from the absolute highest energy and most violent end of the electromagnetic spectrum. So, what cosmic engines could possibly be generating this extreme level of radiation? Astronomers could state one fact with absolute certainty. Whatever the mysterious source was, it was completely invisible to traditional light-based telescopes, and it was unbelievably hot. In physics terms, X-rays can only be generated by cosmic material that has been heated up to blistering temperatures of millions of degrees, or even tens of millions of degrees. One of the very first of these high-energy X-ray sources to completely arrest the attention of global astronomers was discovered in the sky and given the official name Cygnus X1. The naming convention was simple. It was located within the borders of the Swan constellation, Cygnus. It was a pure X-ray source, and it was the absolute first one ever discovered in that region. In the year 1970, a young and ambitious English astronomer named Paul Murdin was working hard to secure his next professional research position. He was currently operating as a young research fellow, but his 3-year employment contract was rapidly drawing to its end. He began to deeply ponder how he could make a definitive historic contribution to the astronomical community by figuring out exactly what these mysterious X-ray objects were. At the time, Murdin was executing his scientific research inside a beautiful 15th century stone castle that was completely surrounded by massive, state-of-the-art observatories. This was a prestigious Royal Observatory. By utilising the single largest telescope in the entire nation of England, he initiated a meticulous, exhausting search of the spatial territory located within the constellation of Cygnus, the Swan. He came up with a clever strategy. He decided to systematically hunt for pairs of stars locked together in space. These stellar pairings are officially designated by science as binary star systems. While they might sound incredibly exotic to the average person, binary stars are actually not uncommon whatsoever in the cosmos. In fact, roughly half of all the glowing stars we can spot in the night sky are actually binaries, consisting of pairs of closely orbiting stars that are permanently locked together by the mutual pull of gravity. Murdin began to wonder if it was theoretically possible for a binary system to exist where only one of the individual stars remained visible to our telescopes. He conceptualized a model where an ordinary normal star that generated standard visible light was orbiting incredibly close to a hidden companion star that exclusively manufactured high-energy X-rays. The single most definitive unmasking sign of a binary pairing is that the two stars are continuously moving around one another in a circular path. Armed with this thesis, Murdin began systematically analysing a visible star in that region to see if it displayed any subtle signs of physical movement. When a star is locked in an orbital dance, its path will periodically bring it directly toward our field of view, and then its orbit will carry it directly away from us. Through the laws of physics, when a star is actively moving toward our position on Earth, the light it emits becomes compressed, causing it to appear slightly more blue in hue. This happens because the wavelength of its light is physically shortened. Conversely, when the star loops around and moves away from us, its light stretches out, causing it to appear slightly more red as the wavelength becomes longer. This foundational wave behaviour is globally known as the Doppler shift. After spending months meticulously scanning and measuring these subtle colour fluctuations across hundreds of individual stars in the Cygnus region, Murdin finally spotted a prime suspect. He located a visible star whose light was continuously shifting back and forth, indicating that it was locked in a rapid orbital loop. It was completely clear that he had located a genuine binary system. His precise data demonstrated that this visible star was whipping around an unseeable centre once every 5.6 days. Yet, no matter how intensely he scrutinised the data, there was absolutely zero trace or signature of a second star appearing anywhere in the recorded light spectrum. There was an ordinary star clearly present, but its mandatory gravitational partner was entirely missing from sight. Murdin had successfully isolated a binary pair where only one single star could be seen. This phantom secondary object was blasting out immense amounts of X-rays and possessed enough raw mass and gravity to violently swing a massive star around it, yet it refused to emit a single photon of visible light. Could this unseeable monster be the heavy corpse of a collapsed star that was massive enough to become a real black hole? The single most critical defining issue in successfully proving whether Cygnus X1 was a genuine black hole or not boiled down to a single mathematical metric: measuring the exact mass of that unseeable X-ray emitting companion. According to the laws of astrophysics, the dark object would have to weigh at least 3 times the mass of our Sun to qualify. If its mass fell below that definitive 3 solar mass threshold, it was highly likely to be nothing more than a standard neutron star, a highly dense collapsed star corpse that is heavy, but simply lacks the necessary weight to collapse space-time into a black hole. Therefore, the global scientific community needed undeniable confirmation that the dark partner in Cygnus X1 was substantially heavier than 3 solar masses. By cross-referencing his orbital calculations, Murdin was finally able to execute a reliable scientific estimate of the hidden partner's true weight. When the mathematics finally settled, the answer came out to a staggering 6 times the mass of our Sun. The data told an undeniable story. Cygnus X1 had to be a real black hole, because the mass of the unseeable star was safely double the maximum threshold allowed for a neutron star. Murdin recalls that the moment he finished writing out all the calculations on his notepad, he leaned back in his office chair and thought to himself, "It is a black hole." This historic conclusion would mark the absolute first time in human history that a real black hole had been successfully detected in the universe. However, because it was such an incredibly massive, paradigm-shifting claim, Murdin knew he would have to battle a wall of intense scepticism, starting with his very own commanding boss at the Royal Observatory, Sir Richard Woolley, who openly disliked the entire concept of black holes. Woolley dismissed the entire theory as highly fanciful nonsense. He grumbled that a bunch of eccentric academics over in California were the ones pushing this wild stuff, noting that there were a lot of bizarre hippie-type individuals operating out in California during that era. He was directly referencing forward-thinking West Coast theoretical physicists like Kip Thorne. Because of this conservative academic environment, Murdin felt incredibly nervous about the sheer scale and controversial nature of the discovery he was about to publish, and his peers felt equally anxious. Murdin was collaborating closely on the project with a brilliant fellow scientist named Louise Webster. Together, they deliberately chose to be incredibly modest and careful about the wording of the official scientific paper they drafted, because they knew exactly how harshly the scientific establishment would react to the claim. If you actually look at the historic paper they ultimately published, the phrase black hole is only mentioned a single time, buried right at the very end of the text, simply stating that they think this object might potentially be a black hole. The landmark Paul Murdin and Louise Webster research paper officially debuted to the public in September of 1971. While a handful of open-minded astronomers agreed that the object could realistically be a black hole, absolutely no one could state it as an indisputable fact. 3 years after the paper's publication, Kip Thorne and the world-renowned British theoretical physicist Stephen Hawking entered into a now legendary scientific wager regarding the true nature of Cygnus X1. They drew up an official contract and made a formal bet on whether Cygnus X1 genuinely contained a real black hole. The wager was conducted partly as a fun joke between friends, as both men deeply hoped that it would turn out to be a real black hole. However, Hawking, employing a bit of reverse psychology because he did not want to jinx the discovery, deliberately bet against his own professional wishes. He formally bet that it was not a black hole. Kip Thorne, on the other hand, signed his name to the claim that it was a real black hole, and they finalised the wager in December of 1974. As the years rolled forward, the global scientific case, proving that Cygnus X1 was a genuine black hole, grew stronger and stronger with every passing month. Finally, in June of the year 1990, while Thorne was away travelling in Russia, Stephen Hawking quietly broke into Thorne's university office, located the original bet document, and stamped his thumbprint onto it, officially conceding the bet and admitting defeat in his friend's absence. Now, while the cumulative astronomical evidence by the year 1990 was certainly robust enough to settle a friendly bet between two legendary physicists, the original mass calculation still suffered from a lack of absolute precision. In order to originally calculate that mass back in the 1970s, Paul Murdin had been forced to rely on highly rough, hand-waved estimates regarding the star's actual distance from Earth, an unmeasured metric that varied wildly by a massive factor of 10. This lingering scientific uncertainty would remain entirely unanswered for another 2 decades, until a dedicated astronomer named Mark Reed became deeply intrigued by the unresolved cosmic puzzle. Operating as a highly esteemed senior astronomer at the Harvard-Smithsonian Center for Astrophysics, Reed set out on a definitive mission to conclusively and permanently prove that Cygnus X1 was a black hole by calculating its exact, unassailable mass. But this goal presented a massive foundational problem. How can you successfully weigh the mass of an entirely unseeable object? By utilising the historical laws of planetary motion originally developed by German astronomer Johannes Kepler all the way back in the 1600s, it is entirely possible to calculate the precise mass of a celestial body. But there is a massive catch. You can only achieve this if you know its exact distance from Earth. In the field of astronomy, distance is absolutely fundamental. If you do not know the exact distance to a cosmic object, you literally have no idea what that object actually is in physical reality. Without distance data, a light in the night sky could be a tiny, weak firefly hovering right in front of your telescope, or it could be a monstrously heavy, colossal star located trillions of miles away that is vastly larger than our own Sun. Therefore, to secure the true, precise mass of Cygnus X1 and permanently confirm its black hole status, Reed required an exact measurement of its distance from Earth. But how can an astronomer accurately measure the distance to a faraway star? The secret to solving this problem lies in a highly familiar visual phenomenon known as parallax. Parallax is the exact optical mechanic that our eyes and brains naturally utilise every single second to perceive the world in 3 dimensions. You can easily test this mechanic yourself right now by simply holding your finger straight up at arm's length in front of your face. Look closely at your finger and then close your left eye. I am currently closing my left eye and focusing on my finger relative to the background wall behind it. Now if I open my left eye and simultaneously close my right eye, I can clearly see that my finger appears to have physically jumped and displaced its position with respect to its original alignment. That visual jump occurs purely because our 2 eyes are physically separated on our face, meaning they are viewing the exact same object from 2 entirely different vantage points. To successfully exploit the mechanics of parallax to measure the distance to an object located in the sky, astronomers let the natural orbital motion of the planet Earth provide the 2 distinct vantage points. Let us visualize that Cygnus X1 is parked at a specific spot in space, while the Earth and the Sun are positioned far away from it. As we know, the Earth completes a full orbital loop around the Sun once a year. In the spring season, the Earth is positioned on one extreme side of the Sun, and we shoot a measurement of Cygnus X1 along a line of sight. Then, exactly 6 months later, the Earth has travelled all the way around to the exact opposite side of the Sun, providing us with a completely different vantage point. By connecting these points, the astronomer has constructed a massive geometric triangle that stretches between the Earth's 2 extreme orbital positions and the distant coordinates of Cygnus X1. We already know the exact width of the triangle's base, which is simply the total diameter of the Earth's orbit around the Sun. Because of this, the basic laws of high school geometry dictate that the only single piece of data we need to calculate the length of the triangle is the precise size of the tiny angle located at the very top peak. If we can successfully measure that minuscule angle pointing at Cygnus X1, we can use direct geometry to effortlessly compute the exact distance to the system. While the conceptual geometry is elegant and simple, executing it is a nightmare, because Cygnus X1 is so incredibly far away that the angle that needs to be measured is completely minuscule, representing a tiny fraction of a single degree. To put its size into perspective, that angle is significantly smaller than the visual angle spanned by Abraham Lincoln's nose on a copper penny located in San Francisco if you were trying to look at it all the way from the city of New York. Because this angle is so incredibly tiny, it is completely impossible to measure it using any single telescope on Earth. But Mark Reed's research team engineered a brilliant solution to this physical limitation. They gathered a network of 10 independent radio telescopes that were widely scattered all across the continental United States, reaching all the way to Hawaii and out to St. Croix in the Virgin Islands. They linked these telescopes together simultaneously, using a powerful computer to synthesize the data into a single, massive virtual telescope that possessed a diameter equal to the physical size of the entire planet Earth. This radical technique instantly granted them an incredible level of angular resolution. By executing this global technique, Reed's team successfully calculated that Cygnus X1 is located exactly 6,000 light-years away from Earth. Armed with this flawless distance metric, they were finally able to compute the system's mass with total precision, revealing that the unseeable object weighs exactly 15 solar masses. This definitive weight placed it easily and undeniably in the category of a real black hole, a full 40 years after it was first identified as a mere theoretical possibility. Cygnus X1 was finally universally accepted as humanity's very first confirmed black hole. It was an elegantly quiet and beautifully understated scientific paper, and the mere fact that my personal name was proudly printed on it alongside Louise Webster's name provided an immense amount of benefit to both of our long-term professional trajectories. I am confident that as a direct consequence of securing this landmark astronomical breakthrough, I was formally extended an offer for a lifelong, permanent research position, which sparked a truly magnificent and joyful celebration throughout my entire family. So the intense effort ultimately yielded wonderful results for my career, which came in addition to the profound internal intellectual fulfillment that naturally accompanies systematically unravelling a major secret of the natural world. So now, at long last, after enduring decades of intense academic doubt and abstract thought experiments, the human race finally possessed undeniable proof of a genuine black hole existing out in deep space. Not only did we have confirmation of its existence, but we had isolated a highly dynamic black hole that was actively radiating immense blasts of high-energy X-rays while locked in a tight orbital embrace with a living companion star. If human beings possessed the capability to travel across the vastness of space and visit this exact system inside my hypothetical starship, what spectacular sights would unfold before our very eyes? Since the exact structural distance separating our planet from Cygnus, X1 has been firmly verified to be precisely 6,000 light-years away from Earth, and its true mass is locked in at exactly 15 solar masses, meaning it holds the physical weight of 15 independent suns compressed together. We can accurately map its anatomy. Cygnus X1 is entirely enveloped by a colossal accretion disk, which manifests as a giant, flattened, disc-shaped cloud composed of superheated gas and interstellar dust swirling just outside the perimeter of its unseeable event horizon, that absolute threshold of no return, as the relentless pull of gravity continuously drags this surrounding matter closer toward the black hole. The entire cloud initiates a rapid, frantic rotation, spinning exactly like water twisting down a narrow drain, deep within the interior zones of that massive accretion disk. The individual material particles that happen to be positioned closest to the unseeable edge of the black hole are whipped around at a blinding rate of speed that equals half the velocity of light itself. It functions exactly like a gargantuan particle accelerator floating out in the void of space. But we must examine the exact physics of why it emits such a ferocious amount of X-ray radiation. As those countless particles race around the orbital track at near-light speeds, they violently collide with one another over and over again, an intense friction that rapidly heats them up to blistering temperatures of millions of degrees. The moment that matter becomes that unimaginably hot, the agitated particles violently erupt with bright streams of high-energy X-rays, and it is precisely those highly energetic X-rays that originally tipped off the brilliant astronomer Paul Murdin, prompting him to investigate this specific black hole nearly 5 decades ago. And there is another highly prominent structural feature regarding the Cygnus X1 system that sets it completely apart from an isolated black hole. It possesses a visible, living companion star. This giant companion star is an ultra-bright blue supergiant, and it completes a full orbital loop around the invisible black hole once every 5.6 days. It maintains an orbit that is positioned so close to the perimeter of Cygnus X1 that the black hole's intense gravitational tide physically strips material directly off the outer atmosphere of the star, pulling that stolen matter directly into the spinning vortex of the accretion disk. A significant portion of that stolen stellar material will eventually slide across the unseeable threshold of the event horizon and get swallowed up into the absolute darkness forever. However, it is an interesting factual reality that not all of the matter suffers that fate. A measurable fraction of the incoming cosmic material actually gets violently redirected and thrown back out into deep space, before it ever possesses a chance of crossing into the interior of the black hole. It is highly reminiscent of a chaotic human toddler attempting to eat a bowl of pasta. Half of the food ends up scattered across the kitchen floor. Another portion might somehow get splattered onto the ceiling, and only a small percentage actually makes it into the child's mouth. One of the absolute most visually striking and profoundly puzzling characteristics of Cygnus X1 is the presence of its colossal, matching energetic jets. These highly concentrated beams, composed of energized particles and intense radiation, stream outward from the north and south poles of Cygnus X1, shooting away perpendicular to the plane of the spinning accretion disk. There still remains an immense amount of data that modern science does not fully comprehend regarding the exact mechanics behind these cosmic jets, but they are known to be tightly focused and features extreme levels of power, blasting out into the void at nearly the speed of light while stretching across distances that extend well beyond the immediate vicinity of Cygnus. When gas is accelerated to these extreme temperatures and generates this brilliant light, a highly localized, intense magnetic field naturally shapes itself around the plasma flow. While we do not yet comprehend the exact details of how it works, these coiled magnetic fields function to tightly channel and collimate these massive outflows venting away from black holes. They act exactly like high-pressure celestial fire hoses that relentlessly spray matter out into the trenches of the universe. So that is exactly what Cygnus X1 would look like if human eyes could view it from an up-close vantage point. It is a continuously growing, actively feeding black hole armed with giant jets that are continuously blasting particles deep out into the surrounding cosmos. They function almost like living, fire-breathing, matter-eating demons of the deep void. They continuously flicker and experience violent energetic bursts, manifesting as a highly turbulent, active, and fiercely chaotic fireball. What was once dismissed as a bizarre, highly eccentric mathematical curiosity trapped inside an abstract equation had finally transformed into a tangible, verified reality. After navigating through multiple decades of intense professional doubt from the academic establishment, scientists now fully accept the fact that the burned-out, collapsed corpses of massive stars can genuinely trap light inside their perimeters, physically warp the geometry of space and time all around them, violently attract surrounding matter, and accelerate it to absolutely mind-boggling speeds. For a long time, black holes seemed like such an incredibly radical and rule-breaking concept that it was completely logical for people to reject it. But step by step, the empirical verification supporting black holes has grown exponentially stronger, revealing these truly amazing phenomena to our instruments. In the modern era, at least 20 confirmed stellar mass black holes have been explicitly identified operating inside our home galaxy alone, existing as visible X-ray binaries exactly like Cygnus X1. And based on statistical mapping, there are highly likely to be millions more of these heavy stellar corpses scattered silently throughout our galaxy alone. Yet, despite this profound level of understanding, a truly stunning surprise was quietly waiting in the wings of astronomical discovery. Every single concept that astronomers believed they understood regarding the nature of black holes, alongside much of what they firmly believed about the birth and evolution of the universe itself, was about to be completely turned upside down by a shocking breakthrough. The historic revelations initiated when global radio telescope surveys of the night sky began detecting highly mysterious, intensely hot spots that were blasting out immense amounts of pure radio energy. When astronomers traced the cosmic coordinates of these powerful radio signals, they discovered that the energy was emanating from objects that looked exactly like ordinary stars to standard light telescopes. Because these newly discovered phenomena closely resembled standard stars, but were exclusively uncovered through their intense radio signals, astronomers chose to name them quasi-stellar radio sources, a clunky phrase that was quickly shortened into the memorable term quasars. But the big question remained: were these strange objects actually a special category of star, or were they something else entirely? The absolute first step in investigating their true identity required researchers to figure out exactly what elements they were made of. To achieve this, astronomers carefully analysed the unique electromagnetic energy that the quasars were actively emitting into space. Every single element on the periodic table possesses a completely unique spectral fingerprint that it imprints onto light, such as the distinct lines generated by carbon, the specific signature left by helium, or the classic markers of hydrogen. These distinct lines, acting as a barcode, reveal the exact chemical blueprint of any star. But when scientists analysed the recorded spectrum of a quasar, the resulting data turned out to be completely incomprehensible and confusing. They looked closely at the readout, and it appeared as absolute gibberish to their eyes. It did not display any recognisable alignment or emission lines from any chemical elements known to science. They were left scratching their heads, wondering what vital piece of the puzzle they were missing. There had to be an explanatory clue hidden somewhere in the numbers. Finally, in the historic year of 1963, a brilliant Caltech astronomer named Martin Schmidt found the golden key hiding in plain sight. Deeply buried within the confusing mess of the quasar spectrum, he spotted the familiar fingerprint of basic hydrogen. He noticed a highly familiar structural pattern of lines, but it was positioned in an entirely incorrect location on the chart. The classic signature of hydrogen had been radically shifted way off to the far red end of the spectrum. It had been incredibly difficult to spot initially because the spectral lines of hydrogen had been stretched toward the lowest frequency end of the electromagnetic spectrum, and that specific physical shift could only mean one definitive thing. The quasar was actively moving away from our position on Earth at a fantastic, near impossible rate of speed. Astronomers had almost never in history witnessed travelling light that had been shifted to such a radical, intense extreme. It functioned exactly like a highly familiar sound pitch, dropping too low for the human ear to easily comprehend. The travelling light arriving from these quasars had been stretched to such a profound degree that the signature of basic hydrogen became completely unrecognisable at first glance. This extreme amount of redshift meant that quasars were actively racing away from our galaxy at blinding velocities. The underlying reason for this universal flight is the ancient legacy of a cataclysmic event that occurred almost 14 billion years in our past: the Big Bang. This was the absolute beginning of our universe, and ever since that initial moment of creation, the universe has been continuously expanding in all directions, carrying along with it every single object it contains, including these mysterious quasars. Virtually no astronomer in history had ever witnessed any object moving away from us at such a blinding velocity, a reality that meant this specific object was operating as the single most distant entity that had ever been observed by human eyes. This vast distance meant that the object itself had to be unimaginably luminous to be seen at all, and science had to find a way to explain that output. It was sitting 2 billion light years away, yet it was continuously pumping out the equivalent energy of 1 trillion suns every single second. What type of engine could possibly generate that level of power? No one in the scientific community had any clear idea what could be powering these monsters, or where this ocean of energy could possibly originate. If you systematically work through the calculations, it becomes clear that it cannot be driven by chemical energy. Furthermore, the math proved that it was entirely impossible to be powered by nuclear energy. There is absolutely no physical way that a quasar could be a standard star, because no amount of stellar nuclear fusion could ever produce that massive amount of star power. The single unique engine in the entire universe that could realistically generate that much raw energy is gravity. It is pure gravity. In our everyday, localized lives on Earth, human beings can overcome the pull of gravity with ease simply by jumping or lifting an object. But when gravity is concentrated to an absolute, radical extreme by the presence of a black hole, it transforms into an overwhelmingly dominant power. A small handful of bold scientists began to wonder if quasars could perhaps be driven by massive gravity engines. What if the colossal energy actively blasting out from quasars is originating directly from intensely bright accretion disks swirling around massive black holes? To produce that specific category of raw energy and that blinding level of cosmic brightness, it absolutely must involve the physics of a black hole. But they realised it could not be just any ordinary black hole. Whatever was driving the extreme emission arriving from a quasar had to be unimaginably massive. How heavy would it need to be? The math indicated it would have to weigh millions or even billions of times heavier than our Sun. It had to be millions or billions of times heavier than the Sun. To contrast this, Cygnus X1 contains only 15 times the mass of the Sun. Therefore, the monstrous black holes powering these distant quasars belong to an entirely distinct, unprecedented category of black hole. They are the supermassives, and based on structural mapping, they appear to be permanently located right at the absolute centres of ancient galaxies. But this realisation immediately prompted researchers to look closer to home and ask about our own galaxy. Could there potentially be a supermassive black hole lurking much closer to home, right inside the Milky Way? The exact geometric centre of our galaxy, which is the unique spot where any hypothetical supermassive black hole would be located, lies in the specific direction of the constellation Sagittarius, the Archer. Now, Sagittarius is not just any random constellation in the night sky. It marks the precise line of sight pointing toward the centre of our own Milky Way galaxy. Because human beings live directly inside the interior of the Milky Way, we cannot look at the galaxy from the outside the way a deep space traveller would. But I can easily activate my trusty, highly advanced imaginary star machine to project the galaxy for us from an outside vantage point. Our cosmic home is a classic spiral galaxy containing hundreds of billions of individual stars that are continuously drawn together by gravity into a gigantic, spinning disk. It is incredibly wide, measuring roughly 100,000 light-years across its diameter, but it is relatively thin, measuring only about 1,000 light-years in thickness, and the entire spiral structure slowly rotates through space. Our solar system is located out here in the suburbs of the disk, and right over here, positioned exactly 26,000 light-years away from the Earth, is the dense core, which we see from our planet in the direction of Sagittarius. In this incredibly packed centre, there are millions of stars crowded together alongside immense clouds of interstellar dust and gas. So that is the comprehensive view of our galaxy from the outside, made possible by our imaginary visualization technology. But since our absolute reality dictates that we live inside the Milky Way, when we look toward the core, we are forced to look through the entire dense plane of our own galaxy, which means it manifests to our eyes as a glowing band of crowded stars and dust arching across the night sky, known to us as the Milky Way. Deep inside this thick band of stars and cosmic dust, could a supermassive black hole be silently lurking? In the decade of the 1990s, a group of determined astronomers became obsessed with solving this exact mystery, wanting to peer directly through the murky smog of the Milky Way to learn what, if anything, was hiding at its absolute centre. One of the lead scientists on this quest was Andrea Ghez. Ghez took on an incredibly daunting and technically challenging experiment. She set out to track the precise movements of individual stars orbiting the exact centre of the galaxy over a span of multiple years. The absolute core essence of this experiment relies on watching stars orbit the centre of the galaxy. Consequently, you want to isolate the specific stars that are positioned as physically close to the centre of the galaxy as humanly possible, which means that I required access to the single largest telescope I could possibly get my hands on, and securing that required me to travel to this extreme location. We find ourselves at the remote summit of Mauna Kea, a giant dormant volcano that rises almost 14,000 feet above the beautiful beaches of Hawaii. This extreme altitude, combined with the incredibly low levels of atmospheric humidity, makes this specific mountain peak the absolute ideal place on Earth for high-end astronomy. This is home to the Keck Observatory, which stands as one of the largest optical telescopes operating in the world. But despite its massive size, Keck suffers from the exact same fundamental limitation that plagues every single ground-based telescope on Earth. That limitation is atmospheric distortion. To understand this effect, think about looking at a tiny pebble sitting at the very bottom of a rushing river. The river water is moving very quickly all around, and your view of that pebble becomes continuously distorted and wavy. Exactly like that rushing river, the Earth's atmosphere is constantly moving and changing, bending incoming starlight exactly like a distorted funhouse mirror. To completely compensate for this physical limitation, Keck pioneered the civil scientific application of a highly complex, once declassified military technology known as adaptive optics. First, they shoot a powerful laser beam high into the night sky, creating an artificial glowing guide star in the upper atmosphere. The turbulent atmosphere immediately distorts the image of this guide star, but a high-speed computer knows exactly what that star should look like if the air was perfectly still, and it calculates the necessary adjustments for the telescope's mirror accordingly. If you look at your reflection in a circus funhouse mirror, your body looks completely distorted and weird. And the primary goal of the adaptive optics system is to introduce a second mirror into the light path that bends into the exact opposite shape, instantly making your reflection look flat and normal again. Deep inside the mechanisms of the telescope, this specialized deformable mirror physically changes its shape up to 2,000 times every single second to completely reverse the distortion caused by the atmosphere. And this system has allowed us to capture the absolute sharpest images ever obtained of the centre of the galaxy. The extreme sharpness of those images allowed Ghez to clearly distinguish individual isolated stars crowded near the core, marking a massive technological advance in history. She initiated the process of recording their exact spatial positions in the year 1995, and every single year since then, we have returned to take an image, simply taking a snapshot. By putting those annual snapshots together in chronological order, it creates a breathtaking time-lapse movie of stellar orbits. And the reality that those movies reveal is completely astounding. The individual stars are whipping around the invisible centre of the Milky Way at phenomenal, frightening speeds. These massive celestial bodies are moving across the void at velocities of several thousand kilometres per second, and in the most extreme cases, they are accelerating up to a staggering 10,000 kilometres per second. If you translate that into standard units, they are screaming along at a blistering 10 million miles per hour. They are absolutely flying across the sky. In order for these giant stars to be travelling at such a frantic rate of speed without being thrown out into intergalactic space, they must be orbiting around something that contains an entirely extreme amount of concentrated mass. The The exact quantity of mass that we mathematically calculate to be sitting at that invisible point is an astronomical 4 million times the mass of our own Sun. What could possibly contain the physical weight of 4 million suns, yet remain entirely unseeable to the most powerful telescopes on Earth? That exact physical paradox stands as the absolute definitive proof of a real black hole. And we are not just talking about a modest stellar mass black hole, but a genuine supermassive monster that is silently resting and sleeping right at the absolute hub of our own home galaxy. In point of fact, this incredible tracking data constitutes the single best empirical evidence obtained by science to date, proving the existence of supermassive black holes not merely inside the core of our own Milky Way galaxy, but anywhere across the entire universe. It is a stunning realization. A colossal, supermassive black hole containing the mass of 4 million suns is sitting directly in the central nucleus of our own Milky Way galaxy. From a broad cosmic point of view, it is positioned right next door to our solar system. And this discovery naturally raises an incredibly deep and profound question for the scientific community. We know that there are literally billions of distinct galaxies scattered across the observable universe. If our home galaxy contains an active supermassive black hole right at its centre, and if distant quasars are continuously discovered residing at the exact cores of their own host galaxies, what about all the other countless galaxies out there in the dark? Are there heavy black holes hiding at the centres of absolutely all galaxies? If they truly reside there, how common are they throughout the wider universe? The reality is that we simply did not possess the data to answer that question. Could astronomers ever realistically hope to systematically identify what specific entities are lurking at the absolute centres of other distant galaxies that are positioned millions of light years away from us, mimicking the precise multi-year star tracking experiment that GES executed inside our own Milky Way? To make that incredibly difficult feat an absolute reality, it would require yet another massive technological innovation operating within the field of modern astronomy. That definitive breakthrough finally arrived when the historic Hubble Space Telescope launched into orbit and initiated the process of delivering crystal clear, pristine images of incredibly distant galaxies, allowing a specialised team of astronomers to immediately get to work. This specific group of researchers eventually became known across the academic community by the nickname the Nukers, a title they earned because their entire scientific focus was completely centred around analysing galactic nuclei, which is the scientific phrase for the dense centres of galaxies. One of the lead astronomers on this elite team is Todd Lauer. He explains that the absolute first step in their operational methodology requires them to capture a highly detailed picture of a target galaxy by utilising the pristine optics of the Hubble Space Telescope. This initial image explicitly exposes exactly where the millions of stars are positioned inside the galaxy, mapping out its broad architectural framework with an exquisite level of visual resolution. However, the golden key to successfully uncovering the hidden presence of a supermassive black hole relies on learning exactly how fast the stars inside that galaxy are moving along their orbital tracks. The major problem is that galaxies situated outside our own Milky Way are positioned much too far away for our instruments to ever track the precise movement of individual isolated stars. But astronomers managed to bypass this limitation by carefully analysing the collective way the light arriving from that galaxy is shifted from blue to red wavelengths at different spatial points across the core. By doing this, researchers can successfully calculate an accurate average speed of the stars orbiting the centre. This velocity data is sufficiently accurate to allow the team to build a flawless digital replica of the galaxy inside a high-speed computer, This critical second step requires the team to systematically model their raw observations. They achieve this by meticulously constructing complex functioning simulations of target galaxies inside the computer environment. This specific programming approach is globally designated as Schwarzschild's method. It was originally engineered by a brilliant Princeton University astronomer named Martin Schwarzschild, who happened to be the direct biological son of Carl Schwarzschild, the legendary man whose historical mathematics first described the theoretical possibility of black holes. Martin Schwarzschild's brilliant programming trick was that his code could successfully build up a highly detailed digital model of an entire galaxy that accounted not only for the precise locations where the physical mass was distributed, but also dynamically simulated exactly how the stars were moving through that mass over time. For every single galaxy that the nukers actively chose to investigate, they painstakingly constructed a dedicated computer simulation from scratch, and then, relying on an exhaustive process of trial and error, they manually adjusted the parameters of mass and orbital velocity. They would run the simulation over and over again, trying to get their computer model to perfectly match the original empirical observations they had captured using the Hubble Space Telescope. They would sit at their terminals and say, "Okay, let us try placing a star right over here. Now let us try inserting another one over at these coordinates. Let us force this one to travel around in this specific direction, and let us make this other one loop around that way." They would execute this tedious programming loop thousands and thousands of times until they had successfully built up a massive virtual library, mapping out exactly how stars can orbit inside that specific galaxy. The ultimate goal of the experiment is to reach a matching point where the simulated observations generated by the computer model perfectly align with the absolute real-world data recorded by the Hubble Space Telescope. But a shocking pattern began to emerge during these runs. That alignment simply was not happening. The computer models were completely failing to match reality. The simulations were clearly missing a vital structural component. They would tweak the code and try it again and again and again, deliberately running the models with 0 black holes inserted at the centre, only to find that they simply could not get the simulated observations to accurately explain the actual data arriving from the Hubble telescope. The mystery was solved only when the programmers manually added an enormous, entirely invisible concentration of mass right at the absolute centre of the digital galaxy. The moment that hidden mass was introduced, the computer model instantly aligned with the Hubble data. In virtually every single scenario, they were forced to insert a massive black hole right at the core to make the simulation work. They literally could not find a way to explain the real-world movements of the stars without including a heavy black hole in the computer model. Out of roughly 36 distinct galaxies that the nukers painstakingly investigated using this method, virtually every single one of them mandatory required the presence of a supermassive black hole at its centre. Since those initial runs, a mountain of subsequent astronomical observations has made the scientific community even more completely certain that supermassive black holes and galaxies are permanently linked together. Every single galaxy where we have possessed the necessary instrument sensitivity to look for one, we have successfully detected a supermassive black hole hiding right at its absolute centre. It stands as a truly stunning, paradigm-shifting revelation. Supermassive black holes, which were once viewed as a completely unexpected, highly anomalous category of object, may actually be a universal feature of nature, residing not merely at the core of our own galaxy, but at the heart of absolutely all galaxies across the universe. Consider the famous galaxy officially catalogued as M31, which is globally known to the public as the Great Andromeda Galaxy. It is positioned roughly 2.5 million light-years away from us, And on a perfectly clear night, it is actually vast and bright enough to be seen with the naked eye from Earth. But even when we point the pristine lens of the Hubble Space Telescope directly at it, we are still entirely unable to view the precise structural details of its deepest interior core. Yet, despite that visual barrier, our orbital models make us completely confident that something unimaginably heavy is hiding out in those central depths. What if human beings possessed the ability to take a significantly closer look at this neighbouring system? What if we could pilot our starship across the void and visit a galaxy located far, far away, as our futuristic vessel officially crosses into the outer spiral arms of the Andromeda galaxy? We are still positioned much too far away to directly witness the specific entity lurking at the absolute centre. However, as we look ahead, we can clearly make out an incredibly dense, tightly packed cluster of millions of stars crowding into the core, a distinct structural signature that strongly hints to astronomers that a giant black hole is residing nearby. If we look back billions of years into the ancient past, this central region would have been completely flooded with massive oceans of gas, crowded stars, and a multitude of smaller black holes. During that violent youth, the central black hole would have actively powered a brilliant quasar, continuously blasting out blinding sheets of radiation across the cosmos. Over a span of hundreds of millions of years, that greedy engine would have systematically consumed all the available gas reserves while swallowing up the closest surrounding stars. If we fast forward to the modern era, the ancient fire of the quasar has completely gone out, leaving behind a sleeping titan. But as we pilot our ship closer to the exact coordinates of the core, we can identify some highly distinctive physical features that humanity has never witnessed before. First of all, the pure physical dimensions of this entity are completely colossal. If you theoretically plucked this black hole out of Andromeda and dropped it directly into the centre of our own solar system, the orbital paths of Mercury, Venus, Earth, and even Mars would all be entirely swallowed up inside the perimeter of its event horizon. That represents a terrifying amount of physical volume, but that scale is absolutely nothing compared to its sheer gravitational weight, which calculates to a staggering 100 million times the mass of our Sun. And the absolute destruction of nearby celestial bodies would not stop at the inner rocky planets. If the planet Jupiter were present, it would not survive for long. The intense gravitational field of this supermassive monster would instantly grab hold of the gas giant, dragging it out of its orbit and swallowing it completely whole. Eventually, Saturn would suffer the exact same violent fate. The distant outer planets might manage to survive the gravitational purge, but they would be left drifting in completely freezing, pitch black, and permanently ruined orbits. Furthermore, this specific supermassive black hole undergoes a highly rapid rotation, spinning furiously on its axis, and in doing so, it aggressively twists and drags the very fabric of local space-time around it like a vortex. Exactly like every single other black hole in the cosmos, the absolute boundary of the event horizon is completely featureless, smooth and blank. You must remember that there is no physical surface or material structure present there. It is simply an unseeable mathematical boundary that permanently conceals the interior from the outside universe. However, the surrounding accretion disk can provide our instruments with an immense amount of detailed data regarding exactly what is transpiring near the boundary. That disk manifests as a blazing fiery ring composed of superheated gas and friction-torn dust circling the perimeter of the black hole. Let us deploy our automated research probes to closely explore the interior zones of the accretion disk. The data indicates that the disk is spinning at an absolutely incredible rate of speed. whipping around the core at as much as half the velocity of light itself. To put that into perspective, if the planet Jupiter were forced to travel at that speed, it would complete its entire multi-year orbital journey around the Sun in just a few short hours. The entire region encircling the supermassive black hole is a chaotic cosmic tornado of extreme physics. We can see that a swarm of smaller stars is caught in this violent whirlwind as well. They function exactly like bright tracers inside a storm, allowing our computers to map out the precise movements of the gravitational currents. The primary robot probe is continuously broadcasting live video images back to our ship's observation screens, following the stellar currents like a high-speed race car speeding around a track. From this up-close vantage point, the extreme warping of local spacetime around the black hole begins to play completely crazy visual tricks on our eyes. As we look at the viewing screen, it appears as though there are two entirely independent accretion disks operating at the same time, one spinning horizontally around the equator and a second vertical disk arcing directly over and under the poles. But the telemetry confirms that this double disk is nothing more than a profound optical illusion. The black hole's extreme gravitational field physically bends the pathway of light rays that are being emitted from the backside of the accretion disk, looping those light paths over the top and under the bottom of the sphere, which makes it look to our eyes as if the disk is simultaneously above and below the centre. In absolute reality, there is zero material orbiting around the poles. It is simply a visual distortion caused by passing light rays. This is the phenomenon of gravitational lensing operating at its absolute limit. If we directed one of our robot probes to draw even closer to the edge of the event horizon, the lensing effect would become so extreme that the probe's forward-facing cameras would look straight ahead and eventually capture a live image of its own structural backside, because the light paths have been forced to travel in an eternal looping circle. So that concludes our up-close tour of the supermassive black hole residing at the centre of the Andromeda Galaxy. It is an entirely amazing and deeply humbling environment to visualise. It is equally amazing to realise that absolutely nothing within the original mathematical equations ever led scientists to imagine that black holes could realistically grow to such a massive scale. As incredibly strange and counterintuitive as they are, ordinary stellar mass black holes were at least explicitly predicted by theoretical models long before they were found. Supermassive black holes, on the other hand, represent a complete and total surprise to the scientific community. In the scenario of stellar mass black holes, researchers mapped them out from a purely theoretical perspective first, and then astronomers went out into the universe and verified their existence through empirical observations. But for the supermassive black holes, that historical timeline was completely inverted. We actually stumbled upon undeniable empirical evidence of their existence observationally first, and now the theoretical physicists are working backward to figure out the code of how these monstrous things could have possibly come into being across the history of the cosmos. We already understand the basic stellar life cycle that allows massive stars to collapse at the end of their lives to manufacture ordinary black holes. But supermassive black holes are larger than those stellar corpses by many orders of magnitude. Cygnus X1 is considered large at 15 times the mass of our Sun, but the supermassive black hole sleeping at the centre of our Milky Way is 4 million times the mass of our Sun. Meanwhile, the monster residing in the Andromeda Galaxy contains 100 million times the mass of our Sun, and it is nowhere near the largest one out there. Astronomers have successfully isolated supermassive black holes that contain a staggering 10 billion, and even 20 billion times the total mass of our Sun. How is it physically possible for nature to manufacture such gigantic black holes? Could these supermassives have originally evolved from the standard collapse of early stars? That scenario seems highly unlikely to modern physicists because we do not know of any stars in the history of the cosmos that could grow billions of times larger than our Sun. We fully understand the physics of the black holes you get from a dying star, which contain a handful of solar masses within their perimeters. But when you are dealing with millions or billions of solar masses, a standard dying star simply cannot have possibly made it. So how did these supermassives, weighing millions or billions of times heavier than our Sun, achieve their size? Did they somehow just grow over time, packing on mass like voracious, unstoppable giants? The wild thing about black holes is that they actively feed. They are continuously devouring any piece of matter that happens to wander within their gravitational sphere of influence, allowing them to grow larger. But how exactly do they execute this growth? What specific items do they eat, and where do they locate their food supplies? We believe that supermassive black holes grow primarily through the steady accretion of gas. The way this works is that you naturally have a vast abundance of gas pooling around in the central nucleus of a galaxy, and this gas will eventually assemble under gravity to form a massive accretion disk. This spinning disk is composed of hydrogen, helium, and a mix of other elements in a gaseous state. The immense gravity of the central black hole continuously pulls this gas inward toward the event horizon. As the gas swirls around the orbital track, it spirals closer and closer to the threshold, and the feeding process begins. The matter trapped in the innermost regions of the disk gets slowly pulled in, accelerated to extreme speeds, and then it hits the event horizon. And that is the absolute end of its journey. Whatever gaseous material successfully drifts past that unseeable boundary of the event horizon simply vanishes from our reality forever. The central black hole has permanently absorbed that specific amount of cosmic matter. Because of this unyielding intake, the swallowed gas directly contributes to the overall weight of the entity, expanding the boundary of the black hole. This represents one definitive pathway through which a black hole can systematically expand its physical size over deep time, gradually nibbling away at ambient gas supplies and floating interstellar dust grains. However, this is far from the only methodology nature employs to feed these monsters. If we look back at our earlier example, Cygnus X1 has been spending millions of years slowly and steadily siphoning material off the outer atmospheric layers of its nearby companion star. This is an incredibly drawn-out, disciplined feeding process that will likely continue unfolding over thousands or even millions of years into the future. But what would happen if a massive black hole could completely shatter an entire living star, ripping it apart in just a matter of a few short years, or even a few brief weeks? That would manifest as an incredibly violent, catastrophic astrophysical event, and a dedicated team of modern space explorers is constantly keeping their instruments on the absolute lookout for such occurrences. We find ourselves inside the Operations Control Center for a highly sophisticated space telescope. The engineers are confirming their tracking data over the radio, stating that they are reading 5 by 5 and showing the official initiation of the tracking window at precisely 0330. They are operating the world-renowned Chandra X-ray Observatory. The mission clock confirms that they have exactly 16 minutes remaining for this tracking segment, which translates to 1/6. Cruising along its orbital path at altitudes that reach up to 86,000 miles above the surface of the Earth, the Chandra satellite is specifically designed to capture hyper-high-resolution images of cosmic objects that exclusively radiate high-energy X-rays. This specific image on the screen represents one of those targets. It displays a short-lived, incredibly energetic, and shockingly violent event known across the scientific community as a transient. This specific category of cosmic explosion completely fascinates an astrophysicist named James Guillochon. He spends his professional career studying events like supernovas, and the systematic destruction of innocent planets by their very own host stars. He openly admits that he is simply completely fascinated with the concept of destroying massive things for the noble advancement of science. In the modern lab, he is actively investigating a highly peculiar cosmic mystery that was originally discovered by an esteemed colleague named Lynn. This glowing pixelated blur displayed across James's computer screen is actually a massive, sudden eruptive burst of pure X-ray energy that was captured purely by accident by our space instruments. This tiny, insignificant smudge originally popped up out of nowhere in the distant background of a completely unrelated research image. But given its extreme distance from our galaxy, the sheer amount of energy required to make it look that bright means it is actually tremendously, mind-bogglingly radiant in physical reality. Could this bright signature potentially be a real black hole caught in the absolute raw act of being born into the universe during the violent crushing death of a gargantuan star? Perhaps that is a valid hypothesis. But there is a major problem with that theory. The intense, blinding radiation that gets unleashed into space during a standard supernova explosion will typically only linger in the sky for a few brief months before fading away into complete darkness. So the team had to ask a critical question. How long has this specific mystery object been continuously blasting out these high-energy X-rays into the cosmos? To accurately uncover that timeline, the researchers had to dig deep into historical archives, looking at older images of that exact same patch of the night sky, captured at earlier calendar dates. They checked the data from the year 2015. Then they analysed the files from 2011. They kept digging, looking at records from 2008. They examined the images from July of 2005. Finally, they reached April of 2005. In that April image, absolutely zero X-rays were detected coming from those coordinates. But a shocking change occurred just 3 months later, in July of 2005. In that image, the X-rays are clearly present, and this powerful, brilliantly bright X-ray signal has continuously maintained its extreme output for more than 10 consecutive years. It has remained fully active from July of 2005 all the way to the present day. That represents a duration that is far, far too long to be explained by a standard supernova explosion. So what could this mystery object realistically be? The physics are clear. A massive black hole that is not actively feeding is completely quiet, dormant, and entirely dark, meaning it will never show up on any telescope in existence. But a black hole that is actively feeding is an entirely different story. The very moment it devours matter, the immense friction blasts out X-rays. So could this smudge be a real black hole that suddenly initiated the process of devouring something completely colossal? What structural effect would this sudden feast inflict upon any object that wanders too close to its perimeter? What would it realistically do to a living star that accidentally drifts past its safety boundary? The answer is that it will literally flay that star alive. It will peel the star apart, layer by individual layer. Ultimately, it will end up completely devouring the entire star. Unlike the modest slow siphoning we witnessed with Cygnus X1, this event is a terrifying 10-year continuous feeding frenzy. It is a massive black hole gulping down an entire star in what amounts to a brief cosmic blink of an eye. This is the direct consequence of a chance orbital collision, transpiring when an incredibly unlucky star happens to wander just a bit too close to the core, allowing the black hole's extreme gravity to physically rip its structure apart. The gravitational pull emanating from the black hole will progressively grow stronger and exponentially more intense as the star narrows the distance. And at that specific threshold, the star will begin to violently deform out of its natural spherical shape. This chaotic phenomenon is officially designated by science as a tidal disruption event. In terms of basic mechanics, it is highly similar to the way our own moon's modest gravity easily pulls and shifts the massive oceans of the Earth back and forth, generating daily tides. Except, the fierce tides generated by a supermassive black hole are literally billions of times stronger and infinitely more destructive. During these extreme events, a star is violently torn completely to shreds by the black hole. Because of this trauma, you can clearly witness a massive plume of bright light radiating across space, which operates as the literal final gasp of the screaming material as it gets stripped from the star. But there is an interesting catch. A specific portion of the star actually possesses a chance to escape the trap, as James demonstrates using a simple visual model in the lab. As the target star gets dramatically elongated and stretched out into a line by the black hole's fierce tidal forces, it will essentially be feeding the black hole at the exact same moment that half of its remaining mass is actively trying to run away into deep space. If we map out the geometry of the stream, everything positioned above this approximate midpoint will actually possess enough velocity to successfully leave the galaxy entirely because it is moving at an absolutely rapid rate of speed. Meanwhile, every single piece of stellar matter positioned below that midpoint will inevitably plummet straight back down toward the event horizon, where it will eventually be completely consumed by the black hole. So this represents another highly effective method for a black hole to rapidly gain an immense amount of weight. Unlike the slow, steady and predictable nibbling behaviour displayed by Cygnus X1, this specific category of black hole is devouring the vast majority of an entire star in one single massive gulp. But whether a black hole chooses to expand its size suddenly by swallowing half a star, or expand steadily through long-term gas accretion, astronomers still run into a massive structural problem when they attempt to mathematically explain how supermassive black holes manage to get so incredibly large so early in the history of the cosmos. This paradox is globally known as the timing problem. The core of the trouble begins when we analyse the very oldest supermassive black holes ever identified by science. These are the ancient quasars, those incredibly bright, unimaginably distant and deeply ancient entities that were first discovered by radio astronomers back in the early 1960s. The great scientific conundrum truly kicked off the moment we started successfully locating these highly specific quasars, which manifest as intensely bright, fully formed supermassive engines operating very early on in the infant timeline of the universe. They are pumping out such a colossal ocean of energy into space that they absolutely must contain an entirely massive amount of concentrated mass. Because these bright quasars are positioned so incredibly far away from our galaxy, looking at them means we are actively looking directly back into the early history of the universe, which originally commenced nearly 14 billion years ago with the Big Bang. These hyper-radiant quasars are actively detected operating just a few 100 million years after the initial Big Bang, which represents a tiny, minuscule fraction of the universe's current age. And despite operating in that ancient infant era, they are already completely enormous. We are talking about black holes that contain a full billion solar masses. These absolute behemoths had to be fully formed and resting in place when the entire universe was only about 550 million years old. Now this timeline presents a massive, impossible problem for standard physics, because you are forced to explain how nature could grow something that incredibly big in that short a span of time. Your models are running directly into absolute physical limitations. The issue is that whether a black hole is slowly nibbling on ambient gas or swallowing a star whole, it turns out that the mechanics of accretion possess a strict universal speed limit. This absolute boundary is named after the legendary English astronomer Sir Arthur Eddington, and the Eddington limit explicitly prevents a black hole from feeding too quickly. This limitation exists because of the intense, blinding light that is continuously blasting outward from its very own spinning accretion disk. As it turns out, travelling light possesses its own physical pressure. Because of this trait, individual photons of light can actually impart a literal physical pushing force onto surrounding matter. We can clearly see this exact physical mechanic playing out in the massive stellar winds blowing away from living stars, where the radiant starlight is physically pushing gas clouds away into space. Consequently, there is a strict mathematical limit to how fast you can realistically feed matter into a black hole, because if you try to dump too much material in at once, the resulting luminosity becomes so intensely radiant that the outward push of the starlight will literally blow the food supply away, instantly quenching and halting its own growth. So if we look at that strict universal speed limit, we are left with a massive mystery. How did those early supermassive quasars manage to get so incredibly big so quickly? Could there potentially be an alternative physical pathway that allows nature to completely bypass the Eddington speed limit entirely? This riddle represents a massive obstacle for astrophysicists, throwing a wrench into our understanding of time itself. How do you successfully grow an object to 1 billion times the total mass of our Sun in a tiny handful of years? What specific environmental conditions do you need to cultivate to trigger that category of rapid growth? A small group of innovative scientists are now asking a radical question. What if there is a natural mechanism that allows a black hole to be born completely massive right from its initial birth? This would grant the entity a massive head start in its growth timeline. If there was a physical mechanism operating in the early universe that allowed a black hole seed to form with an incredibly massive size right from the get-go, then the timing crunch is completely solved, and the growth problem is no longer near as acute. The elegant answer to this riddle, according to a growing number of researchers, is to manufacture a massive black hole directly from a giant cloud of primordial gas. This revolutionary conceptual model is officially designated as direct collapse. The entire process initiates with colossal, pristine gas clouds composed entirely of hydrogen, helium, and the exact same raw structural materials from which ordinary stars are naturally born. Under normal circumstances, the dense interior regions of these massive clouds will begin to rapidly implode under the weight of their own self-gravity. But during a standard collapse, the specific zones of the cloud that are slightly more dense will collapse significantly more quickly than the surrounding regions, and as a direct consequence of these varied speeds, the giant cloud fragments and breaks apart into a multitude of smaller pockets. These isolated fragments will then continue their individual implosions until the internal hydrogen atoms become so tightly squeezed that they begin to merge together. The moment that happens, core nuclear fusion officially ignites, and a cluster of ordinary stars is brought into existence. But the direct collapse model asks a fascinating question. What would happen if a truly gigantic, pristine gas cloud managed to undergo a complete gravitational collapse without ever breaking apart into fragments or manufacturing stars? If you cultivate the exact right physical conditions in the early universe, it would allow a galaxy to form a truly enormous, unified gas disk prior to the birth of any individual stars. As time goes on, this massive gas disk becomes highly unstable, an imbalance that would allow the entire collective mass of the cloud to flow directly into the absolute geometric centre at an incredibly rapid rate of speed, forging a massive black hole instantly. This macroscopic mechanic is actually highly similar to a phenomenon that all human beings have witnessed in the natural world, We can see it playing out in everything from destructive atmospheric tornadoes down to the simple draining of water inside a household bathtub. It is a literal vortex, except in this scenario, it is operating on a supermassive cosmic scale. If you are sitting in a bathtub and you suddenly pull the drain plug out, you can watch the water flowing down in a rapid, spinning vortex directly to the centre. That is the exact cosmic blueprint of direct collapse. Direct collapse represents an incredibly elegant way to manufacture very large black holes early in the history of the universe from massive clouds of gas, completely skipping the traditional stellar life cycle stage entirely, because they would be born entirely large right from their initial creation. These direct collapse black holes would possess a massive structural head start, allowing them to quickly expand into the enormous supermassive quasars that our instruments detect operating in the ancient distant universe. Through this pathway, you could potentially forge these direct collapse black holes with an initial seed mass that is already roughly 10,000 times or even 100,000 times the total mass of our Sun. They are fully formed from the very beginning with that incredible weight. Direct collapse may fully explain how those enormous and early supermassives managed to get their historical start. But this realization immediately opens the door to another highly fundamental question regarding supermassives. What is their true overarching role in the grand architecture of the universe? Is their existence just a random matter of absolute chance? Or are they deeply connected in a massive way to the very framework of the cosmos? Supermassive black holes do not exist in complete isolation out in the void. They seem to live in a permanent, lifelong partnership with their host galaxies. As we know, galaxies are massive collections composed of millions, billions, or even trillions of individual stars that are permanently bound together by gravity. Galaxies operate as the fundamental structural building blocks of our entire universe. So we must ask, are the supermassive black holes sitting at their cores somehow fundamental to their very structural existence? We know for a fact that almost every galaxy we can see contains a supermassive black hole at its centre. It could very well turn out that instead of simply operating as rare cosmic oddities, these entities are a key component to the evolution of the universe. We have arrived at a point in modern astronomy where we realise they likely inhabit the centres of absolutely all galaxies. This universal pattern could realistically only happen if there was a deeply hardwired symbiotic relationship linking the long-term evolution of an entire galaxy to the supermassive black hole residing at its core. What could that universal relationship realistically be? One fascinating clue began to emerge when astronomers measured the mass of galaxies against the mass of their central black holes. They discovered a shocking rule. The larger and more massive a galaxy is, the more massive its central black hole turns out to be. These black holes resting at the centre somehow seem to possess an intimate awareness of their larger scale galactic environment. So the old debate was framed like the classic chicken and egg paradox. Which object came first in history, the host galaxy or the supermassive black hole? But modern data shows it is not near that simple. It appears they somehow grow together in tandem. It is highly difficult for one structure to form completely first and then magically affect the growth of the other. So today, astronomers believe that whatever cosmic mechanism originally manufactured the galaxy had to simultaneously create the black hole as a direct byproduct of that exact same process. Furthermore, there must be an active feedback mechanism linking the black hole to the galaxy that keeps the growth rate of the two structures in lockstep synchronization. The primary way that galaxies expand their size is by continuously forming brand new generations of stars from massive, cooling clouds of hydrogen gas. In basic terms, star formation relies on gas exactly like our cars rely on fuel. If you run out of gas, you completely run out of new stars. So we have to investigate whether these supermassive black holes are somehow actively interfering with the process of star formation inside their galaxies. The data confirms that when a central black hole is actively growing and devouring matter, a tremendous, mind-boggling amount of raw energy is being liberated from the accretion disk and blasted out into the wider galaxy. Astronomers believe that a significant portion of that unleashed energy goes directly to warming up the ambient gas clouds throughout the galaxy. And according to the laws of thermodynamics, gas that becomes too warm will completely fail to collapse, meaning it can no longer form stars anymore. The blisteringly intense heat actively generated by an expanding, ravenous black hole makes it entirely impossible for new generations of stars to physically condense and take shape anywhere near its immediate vicinity. And so, one major, highly definitive pathway through which an expanding supermassive black hole can exert absolute dominance over its surrounding host galaxy is by completely quenching and shutting down the process of star formation. In absolute effect, the long-term growth and energetic behaviour of the central supermassive black hole ultimately determines whether its host galaxy continues to actively expand and flourish or permanently stalls and stagnates out in the dark. These monstrous entities appear to cycle through a highly distinct eating phase, characterised by absolute violent activity, which is followed sequentially by a deeply quiet, calm, and entirely quiescent phase. So they seem to be intricately involved with the structural birth and structural modelling of the surrounding galaxy in that highly specific way, while simultaneously serving to maintain the overall structural stability of the entire galaxy over billions of years. Consequently, these highly mysterious, deeply terrifying, supermassive black holes may actually be the primary agents controlling the physical building of our entire universe. They accomplish this grand architectural feat not necessarily because of their physical volume or localized size, but by the precise method through which the immense amounts of raw energy they generate systematically shapes and sculpts entire galaxies. If you look purely at total mass and count up the collective weight of every single independent black hole operating in the universe, adding the tiny stellar mass ones together with the giant supermassive and hyperviolent ultramassive ones, black holes technically account for very little of the total mass of the cosmos. However, when we evaluate the universe from an energetic perspective, the story changes completely. Precisely how much raw power a galaxy receives, alongside the exact chronological timing of when it receives that energy as it slowly assembles over cosmic time, seems to be entirely dictated and managed by the central black hole. Because of this profound level of systemic influence, they might very well turn out to be the absolute single key players operating across our universe. In the next 2 years, the engineers at NASA are planning to officially launch the highly anticipated James Webb Space Telescope. This instrument will stand as humanity's absolute most powerful, technically sophisticated telescope ever built in human history. The specialised optics of the James Webb are meticulously engineered to peer into the invisible infrared spectrum of light, a technological trait that grants it the unique ability to see significantly farther back into the history of time than the Hubble Space Telescope ever could. This allows it to capture a pristine look at the absolute first generations of stars and pristine galaxies that ever formed in the cosmos right after the initial Big Bang. Astrophysicists harbour incredibly high hopes that the data delivered by the James Webb Space Telescope will successfully help our global community solve many of the remaining, deeply frustrating mysteries surrounding the birth of the earliest supermassive black holes. The primary instrumentation on the James Webb Space Telescope is tuned specifically to carefully observe the highly chaotic environments of the early universe, which was the exact historical epoch when the very first galaxies were being born. Obtaining that pristine data could finally grant human beings a deeply comprehensive understanding of exactly how you end up with a monstrous supermassive black hole resting in the centre of your galaxy to begin with. Interstellar technology is advancing at an absolutely rapid rate of speed, and as a direct consequence of this rapid evolution, our global scientific community is securing really fundamental, completely unprecedented new views of our universe. It is a wonderful time to be alive, and I believe that we are genuinely living right in the middle of a true golden era of modern astronomy, and the highly anticipated James Webb Space Telescope is far from the only major technological project that actively promises to solve some of the deepest mysteries surrounding the nature of black holes. Right now, an entirely separate group of visionary scientists, led by a brilliant researcher named Shep Doeleman, is actively attempting to achieve an event that was once considered completely impossible. They are trying to capture a direct visual picture of a real black hole. It is an incredibly fascinating realization that modern human beings can accurately state any detailed facts about the precise physics of an accretion flow operating right near the threshold of a black hole at all. And if some of this highly predictable linear geometric behaviour manages to survive the extreme warping of spacetime, maybe our computers will have a highly reliable way of accurately interpreting the raw visual data. This historic global initiative is officially designated as the Event Horizon Telescope Project. The baseline, foundational goal driving the Event Horizon Telescope is quite simply to successfully view the unseeable. The team is trying to bring into clear, sharp focus a specific physical phenomenon that mainstream science has told us for many, many decades is precisely an object that human beings can never hope to observe. They are coming directly after the black hole itself. The absolute primary observational target for their global campaign is the object known as Sagittarius A star. This is the monstrous supermassive black hole that resides right at the absolute centre of our very own Milky Way galaxy. To possess a realistic mathematical chance of capturing this target, they are actively linking together a massive global network of independent radio telescopes scattered across the planet. To execute a successful run, the team requires perfectly good weather to manifest simultaneously at 8 entirely different telescope locations positioned all around the world, and that requirement represents an incredibly tall order to secure. But if we look back at the foundational physics of these entities and accept the fact that black holes are completely invisible, we must investigate what exactly these researchers are hoping to photograph. What are they looking for? What we are actively trying to photograph is not the invisible black hole itself, but rather its shadow. As the massive oceans of gas encircling the black hole swirl continuously inward and ultimately strike the perimeter of the event horizon, the unseeable mass leaves a stark silhouette. It casts a very well-defined dark shadow directly against the brilliant backdrop of the superheated glowing light. So when the data is finally compiled, the image should look exactly like a bright donut armed with a perfectly centered, very well-defined dark hole. And that specific donut picture is the exact cosmic trophy that our team is actively chasing after. If I take the raw data and systematically convert it into complex frequencies, I can map it out to pi-square right there on the lab monitor. The research team has successfully conducted their very first global observing run, and they are actively processing the mountain of recorded data right now. They are asking whether you can accurately state the precise velocity of the material. It is deeply hoped that these innovative new tracking technologies will finally grant the human race a completely unprecedented, flawless view of the black holes operating in our universe. But there is one specific, revolutionary new category of technology that is already actively delivering definitive results to the scientific community. And that breakthrough brings our journey directly back here to the facilities of LIGO. This laboratory stands as a monumental main character in the ongoing black hole drama, tracing its operational roots back to a radical physical concept that took hold way ahead of its time, the tracking of gravitational waves. By utilising the complex framework of general relativity, which was his masterpiece theory of gravity, Albert Einstein explicitly predicted that whenever a material object moves through the universe, it can generate physical ripples in the mesh of space and time. This manifests as an absolute real-world squeezing and stretching of space itself. Consequently, one of the single most sought-after holy grails of 20th century physics was to directly detect the presence of these elusive gravitational waves. Achieving that feat was incredibly difficult to do using the mathematics of general relativity, because all the physical effects that you could realistically think of or model were completely infinitesimally small. They were entirely difficult to measure with any traditional instrument. The underlying consensus among the physics community was that if gravitational waves could ever be successfully measured, it would permanently confirm Einstein's ancient mathematical prediction. Furthermore, there could be a massive added benefit to the achievement. It might also simultaneously prove the physical existence of real black holes beyond any lingering doubt. Additionally, it would help researchers solve the massive mystery of how those early supermassive black holes managed to grow so rapidly. But the big question remained: how do you design an instrument that can successfully detect a gravitational wave? In the historic year of 1970, this exact engineering problem caught the complete attention of a brilliant, highly driven young experimental physicist named Ray Weiss. Ray possessed the absolute perfect scientific background to launch a successful hunt for these hidden gravitational waves. For multiple decades prior to this project, he had been actively working with a highly related, much more familiar category of wave dynamics. He was an expert in sound waves. His family were immigrants. They were German Jews who had fled to America, and a large number of their close family friends were deeply, passionately interested in the world of classical music. Ray initially devoted his early career to coaxing every single subtle nuance, tone and detail he could out of recorded musical tracks. But those historical vinyl records suffered from a truly terrible, frustrating engineering problem. Whenever the music playing from the speakers was loud and energetic, it sounded absolutely wonderful to the ear. But the very moment the music became real quiet, slow and delicate, the beautiful notes were instantly drowned out by this annoying sound. It was a continuous, hissing background noise that sounded like shh. And that persistent background hiss was so incredibly annoying to Ray's ears. The critical engineering lessons he painstakingly learned while trying to systematically eliminate background noise in musical recordings would end up paying off massively decades later, when Ray officially turned his scientific attention to the problem of detecting gravitational waves. He explains that we must first deeply understand exactly how a gravitational wave executes its physical work upon the universe. The core problem of measuring gravitational waves requires a totally reimagined approach. It must be generated by a cosmic object that is in some dynamic way moving and actively oscillating. To draw a reliable comparison, a standard sound wave moves by physically compressing and expanding the ambient air particles through which it travels. A gravitational wave, on the other hand, does something vastly more radical. It physically compresses and expands space itself, alongside every single material object contained within that space. If a powerful gravitational wave came tearing directly through the planet Earth, it would cause the literal space of our world to momentarily expand in one direction and then instantly contract back down again. It keeps doing this repeatedly as the wave passes through. It functions just like a geometric distortion that goes back and forth through matter. So how can an engineer accurately measure an incredibly tiny, minuscule expansion and contraction of space itself? Ray's brilliant idea was to utilise the properties of travelling light. His plan was to send a high-powered beam of light from one specific location to another, and then measure the exact duration of time it takes for the light to complete its journey. That outside-in logic is the exact methodology that scientists use to calculate the precise distance separating the Earth from the Moon. They achieve that by bouncing a powerful laser beam directly off a highly reflective mirror that was left behind on the lunar surface by the brave Apollo 11 astronauts. By precisely measuring the exact duration of that round-trip laser journey, scientists could determine the physical distance with total accuracy. Ray engineered an absolutely ingenious design for a specialised instrument that uses lasers and isolated mirrors to detect the faint expansions and contractions of space that would be naturally triggered by a passing gravitational wave. This machinery is officially designated as a laser interferometer. It works by firing a single ultra-pure laser beam directly into a specialised optical block known as a beam splitter. Half of the travelling starlight continues travelling straight ahead down a long vacuum tube toward a distant mirror, while the other half of the light is violently split off at a 90-degree angle and sent down an identical tube toward a second mirror. The distant mirrors bounce the independent light beams back along their paths, where they rejoin at a central photodetector. If the precise physical distances travelled by the two independent beams are exactly the same length, the system is engineered so that the peaks and troughs of the two returning light waves perfectly cancel each other out. Because of this cancellation, the photodetector sees absolutely nothing. You have successfully set the physical trap to measure the gravitational wave. Now comes the moment when a real gravitational wave comes tearing through this massive structure. If a gravitational wave passes directly through the interferometer, it briefly alters the physical length of the vacuum arms. Because the geometry of space has been distorted, the two light beams no longer arrive back at the central splitter at the exact same fraction of a second. They fail to cancel each other out. The moment a gravitational wave hits the facility, a clean signal of light suddenly appears on the photodetector. The trap has been officially sprung. That is the foundational concept of the experiment. It is a very straightforward, clear measurement. It was an incredibly clever idea, and it sounds beautifully simple in principle. But as the old saying goes, the devil lies entirely in the details. And in this specific scenario, so did the Nobel Prize. The physical difference in length triggered between the two massive arms by a passing wave would be completely tiny, beyond anything the human mind can grasp. To visualize how tiny this displacement is, let us take the physical size of a single atom. The measurement we need to make is significantly less than that. Let us go down in size by a factor of 100,000, which lands us at the nucleus of an atom. It is still less than that. It was a full 100 times below the size of an atomic nucleus. So we are talking about a measurement that is really itsy-bitsy, teeny-weeny. The moment people heard the numbers, they thought it was completely crazy. I think nearly everybody's initial knee-jerk reaction to the idea was that this was going to be completely impossible to execute. In the year 1973, Kip Thorne explicitly put his deep professional skepticism on the official academic record inside a classic, world-renowned physics textbook, openly doubting that the experiment would ever work in reality. But at that point in history, Kip had never actually sat down to hear Ray Weiss explain his engineering blueprint in comprehensive detail. The moment they finally met and connected, everything changed. We ended up spending the entire night locked in intense conversation. And during that talk, I realised that it was very possible. Within no time at all, perhaps 20 minutes or half an hour, Kip completely understood the system, and he said, "Yep, this can work." And I ended up eating crow for the absolute rest of my professional career, because once I had talked with Ray about the engineering mechanics in detail, I made a definitive decision that I would spend a large fraction of the remainder of my career doing everything in my power to help the experimenters succeed. It required massive, unprecedented sums of money from funding agencies to successfully bring Ray and Kip's cosmic vision to absolute physical reality. Getting the LIGO facility funded by the government was an extremely controversial, highly volatile academic battle. The directors were asking for hundreds of millions of dollars just to detect a hypothetical signal that had never been seen once in human history. There were many prominent scientists who deeply feared that the massive scale of LIGO would suck all the available research money out of the room, starving other fields of science, though there was an immense amount of professional controversy surrounding the budget. The one thing that everybody on both sides of the aisle could agree on was that this was an extremely mind-bogglingly difficult experiment to pull off. When you build such an exquisitely sensitive instrument, one of your absolute biggest daily operational challenges is Ray Weiss's old hi-fi nemesis, noise. You have to battle continuous ground motion, the seismic rumbling of the earth, acoustic noise from passing cars, and standard sound waves. Absolutely everything in the environment would tend to shake and move that mirror. It turns out that even the absolute emptiness of a total vacuum creates a potentially crippling problem for the mirrors. At these subatomic minuscule distances, the weird, unpredictable randomness of the quantum world creates a continuous ruckus inside the mirrors. This quantum noise is driven directly by quantum fluctuations. At this scale, the massive mirrors are doing exactly what a tiny electron does inside an atom. They are constantly jiggling and vibrating around. To conquer this, they engineered an exquisite level of sensitivity, an extreme vacuum system, and hundreds of thousands of independent electronic circuits. LIGO stands uncontested as one of the single most complex, sophisticated instruments ever designed in the history of human science, and as an absolute final means of completely eliminating the threat of false signals. They built not just one, but two complete independent installations separated by thousands of miles. One facility was constructed in Washington state, and an identical twin was built far away in Louisiana. And so the LIGO designers did it right. They designed more than one detector separated from one another by great geographical distance, so that if you detect a signal in one lab and not in the other, you know to immediately go back and check your electronics. You can verify to make sure it was not just an April Fool's Day prank, and that somebody did not just sneak in and tweak the knobs on the console. In the early fall season of the year 2015, both facilities were officially up and running, but the first official science run had not yet formally commenced. They were still executing final tracking tests. In the quiet, dark, early morning hours of Sunday, September 14, 2015, a dedicated scientist working on site in Louisiana made a fateful, history-altering decision. Robert Schofield had been working tirelessly all weekend inside the lab, executing final system calibrations. He announced over the intercom, "Alrighty, let us take a spectrum measurement." He had one last test to run, saying, "Let us see where this computer is getting its power." But it was late, the hour was draining, and the hardware was simply not cooperating. It was about 4 o'clock or so in the morning, and the team still had about another full hour of calibration work left to execute. They looked at each other, exhausted, and said, "Yeah, things are not working so well, and we are all really tired. Let us not do this last hour or so of work." They chose to call it a night and head home to bed. And exactly 40 minutes later, in the absolute pristine silence of their inactivity, they opened the gateway to human history. A powerful, colossal gravitational wave rumbled directly through both detectors, hitting Louisiana first and then Washington. Had Robert Schofield chosen to work for just 40 more minutes that night, keeping the instruments locked in test mode, a signal that had been travelling through the dark for 1.3 billion years would have been completely wiped out and never recorded. I like to say that one of my absolute biggest contributions to the success of LIGO has been my pure laziness that morning. The next day, I received an urgent email from a colleague saying, "Hey, you need to look at this. Go look at this specific page on the internal web." I opened the link and looked at the chart, and I instantly exclaimed, "Holy cow!" The recorded signal was so incredibly strong that you could easily see the wave pattern by eye right in the raw data. It looked far too good to be true, but it was entirely true. In fact, it was loud, surprisingly clear, and it just sang directly at you, causing the hairs on the back of my neck to stand straight up. The total signal lasted for less than a single second, but in that briefest fraction of a moment, it successfully delivered a cosmically profound message that was more than 1 billion years in the making, permanently and irrefutably proving the existence of real black holes. What we clearly saw in the recorded signal involved a series of oscillations of the mirrors that started out slow at first, and then became faster and faster and faster. This data was precisely the exact behaviour that you would mathematically expect to see from gravitational waves generated by two real black holes spinning around each other, spiralling together into a collision. One black hole contained 36 times the mass of our Sun, while its partner contained 29 times the mass of the Sun. They were whipping around each other hundreds of times every single second, finally completing their ultimate act of mutual destruction by merging into a single body. They forged a single larger black hole of 62 solar masses. The violent merger instantly converted 3 full suns worth of mass into an apocalyptic release of pure energy, far beyond anything ever before witnessed by the human race. In absolute effect, the collision creates an intense storm in the very shape and fabric of space and time. It is exactly as if you had taken 3 independent suns, annihilated them completely from existence, and instantly converted their entire mass into pure gravitational waves. The total output power of this merger was 50 times higher than the combined output power of every single star in the entire universe put together during that fraction of a second. It stands as the most powerful explosion that human beings have ever secured any evidence for in history, with the absolute unique exception of the Big Bang itself. Since that historic first signal in September 2015, LIGO has successfully detected several more collisions of black holes. In October of 2017, Ray Weiss, Kip Thorne, and LIGO's former director, Barry Barish, travelled to Sweden to formally receive the Nobel Prize in Physics. The profound LIGO discoveries prove that black holes can genuinely merge, revealing one clear pathway through which they can grow bigger quickly. Gathering more and more empirical evidence of these merging black holes tells our community that there are a vast number of these stellar black holes scattered throughout space, and that they can successfully locate each other and merge. The discovery opened an entirely new, unmediated methodology for human beings to observe our universe. We had always historically thought of astronomy as a purely visual, observational field, where human beings are looking at electromagnetic radiation, seeing things through light. But this is not radiation. This is something fundamentally different and vastly more profound. These are sort of fundamental tremors vibrating directly through space-time itself. For the first time in history, we can genuinely hear the universe. In August of 2017, astronomers simultaneously saw and heard a major cosmic event for the very first time. LIGO detected gravitational waves arriving from the collision of two neutron stars. While black holes are composed of empty space, neutron stars are dense, material corpses that light up the sky when they smash together. When telescopes and satellites all around the globe pointed their lenses in the direction of the sound, the world witnessed incredible cosmic fireworks. They recorded an explosive collision and a brilliant afterglow, an impact that highly likely resulted in the creation of a brand new black hole. But unless we are lucky enough to observe the exact moment of formation, there remains much we will never know, because so much about black holes is irretrievably out of our reach. We can never look past the event horizon to know their deep history, but we can clearly imagine their ultimate future. The total number of black holes operating in the universe is continuously increasing, and they are steadily getting larger. Stars collapse, black holes feed and merge, and new ones are continuously born. Could it be that one day, trillions of years from now, every single piece of matter in the cosmos will end up trapped inside them, leaving black holes to completely rule the universe? Untold trillions upon trillions of years after that happens, long after the final bits of matter have crossed their event horizons, the laws of quantum mechanics suggest that black holes themselves may slowly radiate away their mass and vanish from this reality forever. Their mysteries remain many, and humanity is just starting to unlock the secrets of these strange, powerful places. But one thing is absolutely certain: black holes will continue to intrigue us, tantalize us, and profoundly challenge both our modern science and our wildest imaginations.